Imagine everything you think you know about the universe, the planets spinning in silent orbits, the stars blazing light across unimaginable distances, the vast galaxies swirling in cosmic dance. This might seem like the full extent of existence, the ultimate scope of reality itself. But what if this is merely the surface, a thin veneer barely touched by our grasp? What if beyond what we can see, hear, or even imagine lies a realm so profound, so enigmatic that it reshapes everything we thought we understood about existence? Join us now on an extraordinary voyage, an expedition that takes us beyond the known universe into the very origins of reality itself. At the heart of this cosmic quest is a question that has puzzled humanity for centuries. What caused the Big Bang? This event, dating back approximately 3.8 billion years, represents the genesis of time, space, matter, and energy, the very foundation of the universe as we know it. From the smallest subatomic particles to the colossal clusters of galaxies, everything traces its roots back to this singular moment. Yet, despite the towering significance of the Big Bang, the mystery surrounding its cause remains an open riddle, a puzzle that has defied the brightest minds. Modern physics proposes that the trigger for this cataclysmic explosion may lie in quantum fluctuations occurring within a tiny, unimaginably hot, and dense point called a singularity. This singularity defies our current understanding of the laws of physics. It is thought to contain all the mass and energy of the cosmos compressed into an infinitesimal space. Quantum theory tells us that even what appears to be empty space is never truly empty. In the vacuum of space, fleeting particles constantly pop into and out of existence, ephemeral by nature, yet significant in their implications. These quantum fluctuations, tiny ripples in the fabric of reality, might have been the spark that ignited the singularity's rapid expansion, unleashing the Big Bang and setting into motion the birth of the universe. This idea, however, dwells at the frontier of scientific knowledge, where the worlds of quantum mechanics and general relativity collide, but have yet to be reconciled. The interplay between these two foundational theories remains one of the most profound challenges in physics. The cause of the Big Bang, therefore, not only beckons as a scientific enigma, but also symbolizes the deeper mysteries woven into the fabric of the cosmos. While the Big Bang theory dominates mainstream cosmology as the most widely accepted explanation for the universe's origin, and evolution, it is not without alternatives. Among the more intriguing is the steady state theory, which challenges the notion of a singular beginning or end. Proposed in the late 1940s, this theory posits that the universe maintains a constant average density despite its expansion by continuously creating new matter. This continuous creation ensures the universe looks the same from any point in time, eternal and unchanging on a grand scale. However, the discovery of cosmic microwave background radiation in 1965 dealt a significant blow to the steady-state theory, providing robust evidence supporting the Big Bang model and causing the steady-state hypothesis to fall out of favor. Yet, its legacy remains a testament to the scientific spirit, a demonstration of how science thrives on questioning, exploring, and refining its understanding of reality. The steady-state theory reminds us of the openness inherent in scientific inquiry, the willingness to entertain diverse hypotheses in our quest to unravel the universe's secrets. Adding further complexity, alternative cosmological models like the Cyclic universe propose a universe that undergoes endless cycles of expansion and contraction. In this vision, the universe expands for a time, then contracts back to a dense state, only to bounce back again in a never-ending cosmic rhythm. This cyclic view enriches our understanding, suggesting that the universe's beginning and end might be part of an eternal dance rather than a singular event. Yet, the question of what existed before the Big Bang propels us deeper into speculative realms, where the boundaries of science blur with philosophy and imagination. According to the Big Bang theory itself, time and space originated at the moment of the explosion, rendering the concept of before meaningless within our conventional understanding. But theoretical physicists have ventured beyond these limits, hypothesizing scenarios like the Big Bounce, where the universe cyclically contracts and expands, or the multiverse concept, suggesting our universe is one bubble among countless others, each with its own laws and constants. These theories push the frontiers of physics into the speculative, drawing upon advanced and sometimes untestable principles in quantum gravity and quantum mechanics. They challenge us to rethink reality, to imagine a cosmos far more vast and complex than our senses reveal. Meanwhile, as we contemplate beginnings, the question of the universe's ultimate fate captivates scientists and dreamers alike. Dark energy, a mysterious force accelerating cosmic expansion, plays a central role in determining how the story might end. Three major scenarios emerge from current understanding. The Big Freeze envisions a future where the universe expands forever. Galaxies drift apart until isolated islands of matter remain, stars burn out leaving a cold, dark void, and entropy reaches a peak, leaving behind a lonely cosmos in eternal frost. The Big Rip takes acceleration to a catastrophic extreme, where dark energy's repulsive force grows so strong that it tears galaxies, stars, planets, and even atoms apart, unraveling the fabric of matter itself in a violent cosmic disintegration. Finally, the Big Crunch hypothesizes that gravitational forces might someday halt the expansion and reverse it, collapsing the universe back into a hot, dense state, perhaps setting the stage for another Big Bang, an endless cycle of creation and destruction. Current observations favor a continuing acceleration, making the Big Freeze or Big Rip the more likely outcomes, but the true nature of dark energy remains elusive. It is this enigma that keeps the fate of the cosmos a closely guarded secret, a mystery still unfolding. Ultimately, these grand theories weave together a vision of a universe not static but dynamic, eternal yet changing, comprehensible yet profoundly mysterious. Each hypothesis invites us to ponder our place in an immense cosmic story, encouraging us to gaze beyond the stars and question not just where we come from, but what lies beyond the horizon of understanding itself, but rather an infinite sequence of dynamic cosmic life cycles. This perspective radically transforms how we understand time and the permanence of the universe itself. Instead of perceiving the Big Bang as a singular, isolated moment that marks the universe's absolute beginning, it emerges as merely one phase in an ongoing, ever-evolving cosmic process. Such a revolutionary idea challenges the conventional notion of a linear progression of time and the straightforward historical narrative of the cosmos that we have long accepted. It proposes a cosmos far more dynamic, complex, and cyclic than previously conceived, where endings and beginnings flow into each other in a perpetual dance of creation and destruction. Furthermore, models of a cyclic universe frequently integrate profound insights from the realms of quantum physics and the elusive theories of quantum gravity. These cutting-edge approaches strive to bridge the long-standing divide between the physics of the very large, governed by Einstein's general relativity, and the physics of the infinitesimally small, described by quantum mechanics. This powerful interplay between the cosmic and the quantum not only aims to redefine our comprehension of the universe's life cycle, but also propels the boundaries of physics into new territories. It inspires novel theoretical frameworks that could one day unify these fundamental forces of nature into a harmonious, all-encompassing picture. In essence, the concept of cyclic universes dramatically expands our conceptual horizons. It invites us to imagine a cosmos where beginnings and endings are fluid, intertwined, and endlessly reborn from the ashes of their predecessors. This cosmic continuum is not a simple start-to-finish narrative, but a grand perpetual cycle in which the universe renews itself time and time again. Such a vision defies our traditional understandings and challenges us to reconsider humanity's place within a far vaster, possibly infinite cosmic tapestry, a continuum that transcends linear time and embraces eternal transformation. Cosmic inflation, a groundbreaking theory proposed in the early 1980s by physicist Alan Guth, revolutionized our understanding of the universe's earliest moments. This theory posits a brief yet stupendously rapid period of exponential expansion that occurred just fractions of a second after the Big Bang. During this infinitesimal fraction of cosmic time, the universe's size ballooned by a staggering factor, possibly greater than 10 raised to the 26th power. The implications of this rapid expansion are profound and multifaceted. First, cosmic inflation provides a compelling explanation for the remarkable homogeneity observed in the universe despite its vastness. The cosmic microwave background radiation, the faint relic light left over from the universe's infancy, is strikingly uniform in every direction we observe. Inflation stretched out any primordial irregularities, smoothing the fabric of the cosmos to produce this uniformity on the largest scales, perfectly aligning with our observations. Second, inflation resolves the horizon problem, a deep cosmological puzzle arising from the observation that regions of the universe separated by billions of light years nonetheless share nearly identical temperatures. Under normal circumstances, such regions could not have exchanged information or energy to reach thermal equilibrium because light would not have had enough time to traverse those vast distances since the universe's inception. Inflation elegantly solves this paradox by suggesting that these regions were once closely proximate before undergoing rapid expansion, allowing them to equilibrate before being flung apart. Moreover, cosmic inflation offers a mechanism for the generation of primordial fluctuations, tiny variations in the density of matter and energy in the early universe. These minute quantum fluctuations were stretched to macroscopic scales by the inflationary expansion and later evolved into the large-scale structures we observe today, including galaxies, galaxy clusters, and the cosmic web itself. Yet, one of the most enigmatic and riveting mysteries confronting modern cosmology is the nature and behavior of dark energy. Currently, dark energy is understood as the dominant force driving the universe's accelerated expansion, yet its properties remain elusive. Is dark energy constant, unchanging over time, or does it vary, growing stronger or weaker? This fundamental question is a subject of intense research and spirited debate, and its answer carries profound implications for the ultimate fate of the cosmos. If dark energy increases in strength over time, it could precipitate a cataclysmic cosmic finale known as the Big Rip. In this extreme scenario, the very fabric of space itself would be torn apart by an ever-intensifying repulsive force. Galaxies, stars, planets, and eventually even atoms would be shredded, ripped asunder by this relentless cosmic force, culminating in a violent and dramatic end. The universe would not fade away quietly, but explode into destruction on the grandest imaginable scale. Conversely, if dark energy diminishes or behaves differently, the fate of the universe might be far more subtle or cyclical, allowing for rebirth and renewal once again. This opens the door to a universe not confined to a single birth and death, but engaged in a continuous cycle of expansion, collapse, and regeneration, echoing the very idea of the infinite cosmic life cycles introduced at the beginning. In this grand tapestry of cosmic ideas, from the cyclic universes to inflation and dark energy, our understanding of existence is both challenged and expanded. We are invited to transcend simple beginnings and endings and to perceive ourselves as inhabitants of a magnificent, ever-changing cosmos, one that is alive with possibility, mystery, and endless transformation. The story of the universe is no longer a single chapter, but an epic, ongoing saga written in the language of space, time, and energy, unfolding eternally across the boundless reaches of the cosmic expanse. But with a catastrophic unraveling of everything that exists, the cosmos might face an unimaginable fate. Conversely, if dark energy were to weaken over time, the universe's grand expansion could slow, come to a halt, or even reverse course. Imagine a universe where the mysterious force pushing everything apart begins to lose its grip, allowing gravity, the age-old cosmic sculptor, to reclaim dominance. In such a scenario, the cosmos could collapse inward in a dramatic cosmic finale known as the Big Crunch. This possible end envisions the universe folding back upon itself, compressing matter and energy into conditions eerily reminiscent of its fiery birth, unimaginably dense and scorching hot. The cosmic stage would be set once more for an event akin to the Big Bang, a rebirth from cosmic ashes. This tantalizing cyclical vision paints a universe caught in an eternal dance of expansion and collapse, death and rebirth, echoing the profound mysteries of time and space. Alternatively, if dark energy remains constant, holding steady as it appears to have done through the observable history of the cosmos, the universe will persist in its relentless accelerated expansion. Galaxies will drift farther apart, slipping beyond each other's grasp as the vast void stretches ever wider. Stars will exhaust their fuel, dimming into remnants of their former glory, while the cosmic temperature plummets toward absolute zero. This chilling outcome, known as the Big Freeze, foretells a universe gradually succumbing to cold, dark emptiness, where time stretches infinitely as energy disperses and life itself struggles to endure. The key to unraveling this cosmic fate lies within the enigmatic nature of dark energy, a force that currently defies full understanding. Scientists hunger for sharper observations and refined theoretical models to illuminate how this force behaves across time. Upcoming missions, equipped with cutting-edge telescopes and detectors, aim to trace the universe's expansion history with unprecedented precision. These explorations could reveal whether dark energy is truly constant, fading away, or perhaps even intensifying, each path unlocking dramatically different cosmic destinies. At the heart of this quest is a profound question. What fundamental laws govern the universe's expansion, and how do they intertwine with the fabric of space and time? The theory of quantum gravity emerges as an ambitious beacon in this pursuit, striving to reconcile the deep contradictions between quantum mechanics, the science of the subatomic, and general relativity, which elegantly describes gravity on the grand cosmic scale. These two pillars of physics, although remarkably successful in their domains, clash irreconcilably at the universe's most extreme boundaries. Where quantum mechanics governs the bizarre and probabilistic dance of particles in minuscule realms, general relativity commands the sweeping curvature of spacetime shaped by massive celestial bodies. Yet, at the Planck scale, the realm of the unimaginably small and energetic, these two frameworks collide, revealing their incompatibility. It is here, at this frontier of knowledge, that quantum gravity seeks to forge a unified path forward. This unification promises not only to bridge the chasm between the very large and the very small, but to unlock the secrets of the universe's earliest moments where the conventional laws of physics falter. The Big Bang itself is shrouded in mystery, traditionally viewed as a singularity, a point of infinite density and temperature where space and time lose meaning. Yet such infinities signal a breakdown in our current understanding rather than a true physical reality. Quantum gravity dares to smooth out these infinities, proposing instead that the universe's beginning may have been a finite, comprehensible state governed by quantum laws. One of the most compelling offshoots of this theory is the concept of a quantum bounce. Rather than emerging from an incomprehensible singularity, the universe might have rebounded from the collapse of a prior cosmos. This bounce would avoid the paradox of infinite density by replacing the classical Big Bang singularity with a quantum transition, offering a continuous cyclical model of cosmic evolution. Imagine the universe not as a one-off event, but as a phoenix, eternally rising from its predecessor's ashes in an unending sequence of collapses and expansions. Each cosmic cycle could birth new galaxies, stars, and perhaps life itself, preserving a cosmic rhythm written in the language of quantum gravity. This vision challenges and enriches our understanding of time, existence, and the ultimate fate of all things. By probing these profound questions, quantum gravity does more than narrate the universe's origin. It shapes the very lens through which humanity comprehends existence. It offers hope that the seemingly chaotic beginning and the universe's uncertain future are part of a grand, interconnected cosmic tapestry. With every observation and theoretical breakthrough, we step closer to unveiling the true story written across spacetime, the narrative of a universe forever expanding, contracting, evolving, and thriving in the eternal mystery of creation, but also challenges our very concept of spacetime and the nature of reality in ways that stretch the limits of human imagination and scientific understanding. While still largely theoretical and grappling with formidable obstacles in terms of empirical validation, advancements in this field hold the tantalizing promise of unlocking answers to some of the most profound and enduring questions about the universe's inception and its fundamental structure. Imagine a universe with no beginning and no end, a concept so radical it upends our traditional views of linear time and unidirectional progression. This idea carries profound implications not only for the physical cosmos, but for our philosophical grasp of existence itself. This vision aligns closely with certain cyclic or eternal universe models, which propose that the universe undergoes an infinite series of expansions and contractions or exists in a perpetual, unchanging state without initiation or conclusion. Scientifically, this concept forces a re-evaluation of the laws of physics as we currently understand them. It implies that the singularity, often regarded as the origin point of everything in the Big Bang model, might not be the absolute beginning, but rather a phase the universe passes through cyclically. Quantum gravity, a realm of physics still largely mysterious, might govern these transitions, weaving together the fabric of spacetime in ways that defy classical logic. This challenges the notion of time as a linear arrow, suggesting instead a cosmos where time is cyclical, or perhaps even an illusion, a mental construct superimposed on a more complex reality. Philosophically and existentially, the notion of a universe with no beginning or end forces us to reconsider the very nature of our existence and the universe itself. It confronts us with a cosmos that is self-sustaining and eternal, eliminating the necessity for a creation event or a prime mover. This has seismic implications for metaphysical debates, particularly those concerned with the age-old question, why is there something rather than nothing? It also shakes the foundations of our understanding of cause and effect, which we usually conceive as linear and temporal. One of the most profound pieces of evidence we have about the universe's earliest moments is the cosmic microwave background, a faint glow permeating all of space. This ancient light is a relic from a time when the universe was merely about 380,000 years old, an infant cosmos barely out of its primordial haze. The cosmic microwave background holds within it profound mysteries about the universe's infancy, its subsequent evolution, and the fundamental physics governing all matter and energy. Firstly, the striking uniformity of the cosmic microwave background, with its temperature incredibly consistent across the sky, reveals the universe's homogeneous nature at early times. Yet this uniformity presents the horizon problem. It raises the perplexing question of how regions of the universe, now billions of light years apart, were once in thermal equilibrium despite seemingly not having enough time to interact. This mystery points toward the concept of inflation, a hypothesized rapid expansion of the universe immediately after the Big Bang that could explain this uniformity. Moreover, the tiny temperature variations within the cosmic microwave background, minute fluctuations as small as 1 part in 100,000, hold clues about the early distribution of matter and the seeds of cosmic structure. These minute anisotropies provide a foundation for understanding how galaxies and clusters of galaxies formed over billions of years, evolving from initially tiny quantum fluctuations in the fabric of spacetime itself. By analyzing these temperature anisotropies, scientists have been able to determine the universe's age, geometry, and composition, including the enigmatic dark matter and dark energy that together make up roughly 95% of the cosmos but remain largely mysterious. The polarization of the cosmic microwave background, a more subtle and delicate feature, offers insights into the universe's first moments and the potential for primordial gravitational waves generated during inflation. Such waves could open a new window into the study of quantum gravity and help us understand how the large-scale structure of the universe emerged from the interplay between quantum mechanics and general relativity. Finally, the cosmic microwave background challenges us with anomalies that do not neatly fit the predictions of the standard cosmological model. One such anomaly is the cold spot, a region of the sky colder than surrounding areas, sparking ongoing investigation and debate. These features hint that our current understanding of the cosmos is still incomplete, and that new physics may await discovery beyond the horizons of our existing theories. In essence, the cosmic microwave background serves as a cosmic time capsule, encoding the universe's birth, its accelerated expansion, and the intricate dance of matter and energy that has shaped everything from the smallest atoms to the largest galaxy clusters. Unraveling these enigmas not only deepens our knowledge of the cosmos, but also challenges our very understanding of reality itself. This journey of discovery leads us down pathways where science meets philosophy, where quantum mechanics collides with the vastness of space-time, and where the universe's mysteries beckon us to rethink what we believe about existence, time, and the cosmos in its entirety. The questions raised by these ideas do not have easy answers, but they propel humanity's relentless quest to comprehend the ultimate nature of everything that is, was, and ever will be. but also propels forward the frontiers of physics, urging us to confront the deepest and most profound questions about the very nature of reality itself. Dark matter, an invisible substance believed to constitute about 27% of the total mass and energy of the universe, remains one of the most tantalizing and enduring mysteries in modern astrophysics. Though it escapes direct detection, its existence is unmistakably inferred through its gravitational effects on visible matter, affecting stars, galaxies, and even the cosmic microwave background, the afterglow of the Big Bang itself. Scientists have long sought to understand what this elusive dark matter could be. Several leading theories propose a variety of fascinating candidates. Among the most prominent are weakly interacting massive particles, or WIMPs. As their name suggests, WIMPs interact very weakly with ordinary matter, primarily through the force of gravity. The idea of WIMPs emerges naturally from extensions to the standard model of particle physics, such as supersymmetry, which predicts new particles that could fit the bill. Their appeal lies not only in their theoretical elegance, but also in their ability to potentially explain dark matter's behavior at galactic scales, seamlessly connecting the microcosm of particle physics to the vast cosmic landscape. Another compelling candidate is the axion. Axions are theorized particles much lighter than WIMPs, originally proposed to solve a thorny problem in quantum chromodynamics, the strong CP problem. Unlike WIMPs, axions would interact extremely weakly with electromagnetic fields, making them extraordinarily difficult to detect, but potentially abundant throughout the universe. If axions exist, they could form a pervasive, unseen web underlying all cosmic structures. Sterile neutrinos represent yet another intriguing possibility. These hypothetical neutrinos differ fundamentally from the three known types in the standard model, as they do not participate in weak nuclear interactions, earning them the sterile label. Their existence could simultaneously shed light on the nature of dark matter and resolve puzzling anomalies observed in neutrino mass measurements, intertwining two of physics' greatest enigmas. Beyond these candidates lie even more exotic and speculative possibilities. Primordial black holes, tiny black holes formed in the dense conditions of the early universe, could account for some fraction of dark matter. These black holes would be relics from the dawn of time, silently drifting through the cosmos, their gravitational influence shaping galaxies and clusters. Dark photons, hypothetical particles mediating interactions within a hidden, dark sector, represent yet another frontier. Analogous to how ordinary photons carry electromagnetic forces, dark photons could unlock an entirely new realm of physics, invisible to our current instruments, but no less real. Each of these theories carries profound implications, not only for the identity of dark matter, but also for the fundamental laws that govern our universe. They push the boundaries of human knowledge, demanding ever more sensitive experiments and groundbreaking observations. Cutting-edge particle accelerators, state-of-the-art telescopes, and vast cosmic surveys all play pivotal roles in this quest. They are designed to capture the faintest whispers of interaction between dark matter and ordinary matter to finally unveil the nature of this cosmic shadow. Detecting dark matter directly has proven extraordinarily challenging, precisely because of its defining property. It does not interact with electromagnetic forces in any significant way. Unlike ordinary matter, dark matter neither absorbs, emits, nor reflects light, rendering it invisible to conventional optical instruments. Instead, its presence is discerned through its gravitational effects, the anomalous rotation curves of galaxies that defy Newtonian predictions, the gravitational lensing that bends light around massive objects, and the subtle imprints left on the cosmic microwave background radiation. The leading dark matter candidates, WIMPs, axions, and sterile neutrinos, interact so feebly with ordinary matter that their detection hinges on extraordinarily rare events. For example, a WIMP or axion might collide with a nucleus inside a specially designed detector in just the right way to leave a faint observable signal. The expected frequency of such interactions is vanishingly small, which means that detectors must be extremely sensitive and carefully shielded from background noise, such as cosmic rays or natural radioactivity, which could produce false signals. Because the properties of these particles, their masses, interaction strengths, and other characteristics are largely unknown, experimental searches must scan a broad parameter space. This uncertainty complicates the design of experiments, requiring a variety of approaches, from deep underground laboratories shielded from cosmic rays to large-scale detectors buried underwater or beneath ice sheets, each employing different materials and technologies to catch these ghostly particles. Despite decades of searching, direct detection remains elusive. Yet this has not been a failure, but rather a process of refinement, as each experiment narrows down the properties that dark matter could have. These constraints guide theorists and experimentalists alike, pushing them to innovate with ever more sensitive technologies and sophisticated data analysis techniques. The enigmatic nature of dark matter reflects its unique and subtle interaction with the fundamental forces. It challenges physicists to venture beyond the well-trodden paths of the standard model into realms where new particles and forces may reside, hidden from view but shaping the cosmos on grand scales. The search for dark matter drives the development of cutting-edge detectors and inspires new theoretical frameworks, each step pushing the frontier of knowledge a little further. Parallel to the mystery of dark matter is the puzzle of dark energy, a mysterious force driving the accelerating expansion of the universe. This phenomenon was discovered in the late 1990s through meticulous observations of distant supernova, revealing that, contrary to expectations, the universe is not slowing its expansion under gravity's pull, but instead speeding up. The fabric of space-time itself appears to be stretching at an ever-increasing rate. Dark energy comprises roughly 68% of the universe's total energy budget, dominating its large-scale dynamics. Its exact nature remains one of the most profound and enigmatic questions in cosmology. Various hypotheses attempt to explain dark energy, from a cosmological constant, a fixed energy density inherent to space itself, to more dynamic forms like quintessence, involving fields that evolve over time. Understanding dark energy demands not only advanced observational campaigns using powerful telescopes and space-based observatories, but also new theoretical insights that may revolutionize our understanding of gravity and space-time. Like dark matter, dark energy beckons scientists to explore the unknown, promising to reshape our comprehension of the cosmos. Together, dark matter and dark energy compose the unseen majority of the universe, painting a picture of a cosmos dominated by mysteries that challenge our most fundamental assumptions. As researchers push forward with innovative experiments, harnessing the latest technology and the collective intellect of the global scientific community, humanity edges closer to uncovering the true nature of these dark constituents. Their discovery would not only solve long-standing puzzles, but also unlock new paradigms, altering the course of physics and cosmology forever. But it is broadly characterized as a mysterious form of energy that pervades every corner of the cosmos, an unseen force weaving through the fabric of space itself. This enigmatic energy exerts a peculiar and powerful repulsive force, a cosmic push that defies gravity's familiar pull. This repulsive force is not merely a curiosity. It is the driving engine behind one of the most profound discoveries in modern astrophysics, the accelerated expansion of the universe. The revelation that the universe's growth is speeding up shook the foundations of science, opening the door to a host of new questions and theories about the true nature of reality. There are several leading contenders in the quest to understand this cosmic mystery, each proposing a distinct vision of dark energy's essence and behavior. One of the earliest and most enduring ideas is the cosmological constant, a concept introduced by Albert Einstein himself during the early days of his general theory of relativity. Originally, Einstein conceived the cosmological constant, symbolized by the Greek letter lambda, as a mathematical fix to allow for a static, unchanging universe, a notion later discarded when the universe was found to be expanding. However, this constant has been resurrected to explain the accelerating expansion. In this view, dark energy is a steady, unchanging energy density filling space uniformly, providing a constant outward pressure, a cosmic force steadily pushing galaxies apart and accelerating the universe's expansion with relentless consistency. 2, however, challenges this picture with a more dynamic and evolving interpretation known as quintessence. Unlike the static cosmological constant, quintessence envisions a shifting, mutable field that changes its energy properties over time and space. This fluid and evolving field could cause the rate of cosmic acceleration to vary, producing periods where the universe's expansion speeds up or slows down, weaving a far more intricate tapestry of cosmic evolution. Quintessence introduces a tantalizing complexity, implying that dark energy is not fixed but mutable, its strength waxing and waning over the eons, subtly shaping the cosmic landscape and the destiny of all matter within it. Regardless of which theory ultimately holds true, the implications of dark energy's contribution to the accelerated expansion are profound and far-reaching. It suggests a future where galaxies will continue to drift apart at an ever-increasing pace, becoming isolated islands in an increasingly cold, dark, and lonely cosmos. The fabric of space stretching ever wider implies a cosmic fate that may culminate in an eternal, frigid void, where stars exhaust their fuel and galaxies disappear beyond the observable horizon. To unlock the secrets of dark energy and its cosmic role, scientists have embarked on an ambitious and multifaceted campaign of research, employing some of the most sophisticated instruments ever built. Observational programs and experiments span the globe and extend into space, each designed to probe different facets of these invisible forces that govern the universe. On Earth, massive underground detectors such as the Xenon experiments and their successor, the Lux Zeppelin (LZ experiment), delve deep beneath the surface to shield themselves from the interfering noise of cosmic rays and natural radiation. These experiments focus on the elusive dark matter counterpart, seeking to directly detect the rare and faint interactions between dark matter particles and ordinary matter, providing crucial insights into the unseen mass that shapes galaxies. Complementing these terrestrial efforts are indirect detection projects that scan the heavens for cosmic signals, high-energy cosmic rays and gamma rays that might arise when dark matter particles annihilate or decay in the vast expanses of space. Instruments like the Fermi Large Area Telescope and the Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station vigilantly watch for these subtle signatures, seeking clues in the cosmic radiation background. Meanwhile, particle colliders, such as the Large Hadron Collider, LHC, at CERN smash particles together at near-light speeds, hoping to create dark matter particles in the laboratory, offering a direct window into their properties and behavior. This grand symphony of experimental approaches spans from the subterranean depths to the high-energy frontiers of particle physics, each method a vital piece in the puzzle. Turning the gaze back to dark energy itself, projects like the Dark Energy Survey, DES, harness the power of a 570-megapixel camera mounted on a telescope in Chile to capture the faint light of distant galaxies and exploding supernovae, mapping their distribution and movement across the sky. The goal is to measure how dark energy influences cosmic expansion and the formation of large-scale structures over billions of years. Alongside DES, the European Space Agency's Euclid mission charts the dark universe with precision by measuring galaxy redshifts and the subtle bending of light caused by gravitational lensing, aiming to uncover the geometry and expansion history of the cosmos. Expanding observational horizons even further, the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, is set to undertake a decade-long comprehensive survey of the sky, capturing detailed and frequent images that will generate an unprecedented wealth of data. This monumental dataset promises not only to deepen our understanding of dark energy, but to revolutionize astronomy across numerous fields, enabling discoveries yet unimagined. Together, these cutting-edge efforts weave a narrative of human curiosity and technological prowess, pushing the boundaries of knowledge to decipher the ultimate mysteries of dark energy and dark matter. Their findings will not only illuminate the cosmic past and future, but may compel us to rethink fundamental physics, challenging long-held assumptions, and inspiring new paradigms in our quest to comprehend the vast and mysterious universe in which we live. But also for exploring dark matter by tracking how billions of galaxies and cosmic structures evolve over time, these experiments and missions collectively represent a monumental chapter in humanity's quest to unlock the deepest secrets of the universe. Scientists are embarking on an extraordinary journey, where each observation, each data point, peels back another layer of the cosmic veil, gradually revealing the hidden forces that govern existence itself. Through a blend of direct detection, indirect observation, and advanced simulations, the global scientific community stands united in a mission that transcends borders and disciplines, working tirelessly to decipher the mysteries of dark matter and dark energy. But the story of dark matter and dark energy is not just one of discovery. It is also a saga of profound enigma and cosmic wonder. These two elusive entities, which together account for roughly 95% of the universe's total content, remain stubbornly beyond the reach of direct observation. They manifest not as shimmering lights or detectable particles, but as subtle gravitational whispers and accelerating cosmic expansion. This paradox has propelled scientists to rethink their fundamental understanding of the universe's architecture. And yet, despite their invisibility, dark matter and dark energy play the role of unseen architects, sculpting the grandest structures in the cosmos. Dark matter forms an invisible scaffold, a vast cosmic web upon which galaxies are delicately hung like beads on a string. Without this invisible glue, galaxies would spin apart, unable to hold their form against the centrifugal forces generated by their own rotation. Observations of galaxy rotation curves and gravitational lensing have long hinted at this unseen mass, forcing astronomers to conclude that the ordinary matter visible to telescopes is but a fraction of the universe's true mass-energy content. Dark energy, on the other hand, behaves like a mysterious cosmic force, pushing the universe's fabric outward, accelerating its expansion in ways that defy classical gravity. This force permeates all of space, silently driving galaxies further apart and reshaping the universe's destiny. The interplay between dark matter's gravitational attraction and dark energy's repulsive push forms the cosmic dance that weaves the vast and intricate, large-scale structure of the universe. The cosmic web, an interconnected network of galaxy clusters, filaments, and enormous voids stretching across unimaginable distances. But there is more to the story than the standard cosmological model. Some scientists challenge the very existence of these dark components by exploring alternative explanations rooted in fundamental physics. One such idea, known as modified Newtonian dynamics, MOM, proposes that the law of gravity itself might require revision at cosmic scales and very low accelerations. According to this theory, the anomalies attributed to dark matter might instead arise from a modified gravitational force, eliminating the need for invisible mass. Similarly, emergent gravity theories suggest that what we perceive as dark matter's influence could be the result of quantum effects in the vacuum, subtly altering the behavior of gravity on galactic scales. These alternative frameworks invite us to rethink the nature of gravity and question the foundations of physics, driving a deeper investigation into the universe's fundamental laws. While speculative, they broaden the horizons of scientific inquiry and underscore how much remains unknown about reality's true nature. Scientists continue to harness the power of cutting-edge observatories and particle detectors, spanning the electromagnetic spectrum from radio waves to gamma rays, while deploying space-based telescopes and underground experiments. Each instrument offers a unique vantage point, capturing different facets of these dark phenomena. Missions like the Vera C. Rubin Observatory, the Euclid Satellite, and the Dark Energy Survey collectively gather billions of data points, tracking the subtle evolution of cosmic structures over billions of years. Through this data, researchers reconstruct the story of cosmic expansion and structure formation with unprecedented detail. The discovery of dark matter particles would mark a watershed moment in physics. It would transform dark matter from an abstract theoretical concept to a tangible entity within our grasp, opening new chapters in particle physics, cosmology, and beyond. This breakthrough would confirm decades of astrophysical observations and refine our understanding of the universe's origin, evolution, and ultimate fate. The stakes could not be higher. Understanding dark matter and dark energy is not merely a scientific curiosity, but a quest to comprehend the very fabric of reality. The answers hidden within these dark components hold the key to fundamental questions. How did the universe begin? What forces govern its expansion? What is the destiny of all cosmic structures? As scientists push the boundaries of knowledge, each discovery brings us closer to unveiling the majestic, invisible forces shaping everything we see and everything we have yet to see in the vast, mysterious cosmos, but also expand the standard model of particle physics, which currently does not accommodate dark matter. Unveiling the nature of dark matter particles could lead to a deeper comprehension of the forces that govern the universe, possibly uncovering new physics beyond our current theoretical frameworks. It might pave the way for unified theories that reconcile quantum mechanics with general relativity, offering insights into the earliest moments after the Big Bang and revealing the mechanisms behind galaxy formation and evolution. Furthermore, understanding dark matter could have profound implications for technologies dependent on fundamental physics, potentially leading to advancements in fields as diverse as quantum computing, energy generation, and material science. In essence, the discovery of dark matter particles would be a cornerstone in the quest for a comprehensive understanding of the cosmos, reshaping our knowledge of the universe and our place within it. The elusive nature of dark matter and dark energy means that there may indeed be observable effects or signatures that have thus far gone undetected or misinterpreted within the cosmic tapestry. Given that dark matter does not emit, absorb, or reflect light, its presence is inferred primarily through gravitational effects on visible matter, such as the rotation curves of galaxies and gravitational lensing. Meanwhile, dark energy's influence is perceived through the accelerated expansion of the universe. However, these known phenomena might only be the tip of the iceberg regarding how dark matter and dark energy interact with the observable universe. Astrophysicists continually refine their instruments and methodologies, hoping to uncover subtle cues that have been overlooked. For instance, anomalies in the cosmic microwave background radiation or irregularities in the distribution of galaxies could hint at previously unrecognized influences of dark matter and dark energy. Additionally, advanced simulations of the universe's evolution incorporating dark matter and dark energy might reveal discrepancies with observations, suggesting alternative behaviors or interactions. The James Webb Space Telescope, with its unprecedented sensitivity and resolution, could detect faint signatures that hint at the dynamics of dark matter and dark energy within the early universe. Ultimately, identifying these missing observable effects would necessitate a combination of innovative technology, novel theoretical frameworks, and perhaps a bit of serendipity. Any new findings could significantly alter our understanding of the universe's composition and evolution, offering fresh insights into the fundamental laws of physics. Galactic phenomena have posed intriguing challenges to our understanding of dark matter, often forcing scientists to reassess their theories about this mysterious component of the universe. One of the most compelling puzzles is the discrepancy between the predicted distribution of dark matter in galaxies based on simulations and what is observed through astrophysical measurements. According to the prevailing cold dark matter model, dark matter should be densely packed at the centers of galaxies, forming a steep cusp. However, observations of the rotational speeds of stars and gas in many galaxies suggest a much flatter distribution known as a core. This cusp core problem raises questions about the nature of dark matter and the processes involved in galaxy formation and evolution. Another challenging phenomenon is the observed behavior of satellite galaxies as orbiting the Milky Way and other galaxies. These satellite galaxies tend to be arranged in vast, thin planes and move coherently, a configuration that is difficult to reconcile with the random distribution of satellite galaxies predicted by simulations based on the cold dark matter model. This puzzling arrangement, often referred to as the plane of satellite galaxies problem, suggests that there could be fundamental aspects of dark matter or the forces acting upon it that are not yet understood. Furthermore, the discovery of galaxies that appear to lack dark matter entirely, such as NGC 1050F2, challenges the very notion that dark matter is a necessary component of all galaxies. These anomalies invite a closer examination of the laws governing dark matter and its role in cosmic structure. Together, these phenomena suggest that either our understanding of dark matter is incomplete or that additional physical processes are at play within galaxies. As scientists continue to investigate these galactic mysteries, they inch closer to unraveling the true nature of dark matter, potentially transforming our comprehension of the universe itself. The dark sector, comprising dark matter and dark energy, plays a pivotal role in the formation of cosmic structures, driving the evolution of the universe from its earliest moments to the intricate cosmic web observed today. At the heart of this process is dark matter, which clumps together under the influence of gravity, forming the scaffolding around which visible matter congregates. In the infant universe, slight density fluctuations, possibly imprinted by quantum fluctuations during inflation, served as seeds around which dark matter began to coalesce. These dark matter halos attracted gas and dust, leading to the formation of stars, galaxies, and eventually galaxy clusters and superclusters woven into the vast cosmic web. Dark energy, with its repulsive force, influences the large-scale structure of the universe by driving its accelerated expansion. This expansion affects the destiny of cosmic structures, determining the rate at which galaxies move away from each other and the ultimate fate of the universe. While dark matter pulls matter together, dark energy works to tear it apart, creating a cosmic tug-of-war. The interplay between these dark components governs the pace of structure formation, with dark matter dominating in the early universe, enabling galaxies and larger structures to form before dark energy's influence becomes significant, altering the dynamics of cosmic expansion. As our technological capabilities advance, the quest to understand dark matter and dark energy intensifies. Cutting-edge particle detectors deep underground aim to capture elusive interactions between dark matter particles and ordinary matter. Experiments at particle accelerators like the Large Hadron Collider seek evidence of new particles or forces linked to the dark sector. Meanwhile, astronomical surveys map the distribution of galaxies and the cosmic microwave background with ever-increasing precision to test and refine cosmological models. The complexity of dark matter and dark energy challenges not only observational techniques, but also theoretical physics. The Standard Model, though immensely successful in describing known particles and interactions, lacks provisions for dark matter candidates. This gap fuels research into supersymmetry, extra dimensions, axions, sterile neutrinos, and other exotic possibilities. Theoretical breakthroughs could revolutionize physics, bridging quantum mechanics and gravity, unlocking the secrets of the universe's birth and fate. In summary, dark matter and dark energy are more than mysterious components of the cosmos. They are the keys to unlocking the fundamental workings of nature. Their discovery and study stand to transform our understanding of physics, cosmology, and even technology itself. The journey to comprehend these unseen forces continues to inspire and challenge scientists, driving humanity's quest to unravel the deepest mysteries of existence and our place in the vast, ever-expanding universe. And so begins the cosmic saga, an intricate dance unfolding in the dark between dark matter and dark energy, two enigmatic forces shaping the very architecture of our universe. Dark matter, invisible yet omnipresent, and dark energy, a mysterious force accelerating cosmic expansion, together dictate the grand distribution and evolution of galaxies across the vast expanse of cosmic time. This interplay is no mere background drama, but the fundamental scaffold supporting the cosmic web where galaxies cluster and evolve. Grasping the role of this dark sector is essential, a key to unlocking the universe's history and its destined future trajectory. The story of the cosmos is incomplete without unveiling the secrets held tightly by dark matter and dark energy, the shadow architects of all that we observe, yet barely understand. And deep within this vast cosmic tableau lies one of the most profound mysteries known to science, inside a black hole. Here, in the cloaked heart of darkness, physics as we know it collapses into uncertainty. At the core of every black hole resides the singularity, a point where matter is crushed into infinite density, and gravity's grip becomes so intense that nothing, not even light, can escape its grasp. Space and time themselves contort into an infinitely steep curvature, warping reality in ways that challenge our comprehension. General relativity paints a picture of this singularity as a place where the very fabric of space-time ends, but this classical view clashes with the quantum mechanics that governs the microscopic realm. The singularity remains a profound enigma, a place where current theories falter and diverge, offering tantalizing glimpses but no definitive answers. Moreover, the notion of the information paradox proposed by Stephen Hawking adds another layer of mystery to black hole interiors. This paradox suggests that the information contained within matter swallowed by black holes seems to vanish from our universe, defying the fundamental quantum principle that information cannot be lost. The paradox challenges our deepest understanding of reality, posing questions that ripple through fields of physics and cosmology alike. Black holes are, in essence, the universe's ultimate laboratories for extreme physics, pushing the boundaries of what is known and inviting new theories that seek to unify quantum mechanics and general relativity. A unified theory of quantum gravity, possibly embodied in frameworks like string theory or loop quantum gravity. And the saga continues with the colossal titans of the universe, supermassive black holes. These cosmic behemoths lurk at the centers of most large galaxies, including our very own Milky Way, their origins cloaked in mystery and fierce scientific debate. Unlike stellar black holes born from the explosive deaths of massive stars, the birth of supermassive black holes is less straightforward, potentially following multiple intertwined pathways. One prevailing theory proposes that these giants began as seeds formed from the direct collapse of enormous clouds of primordial gas in the young universe. Under their own immense gravity, these clouds could have compressed into black holes containing hundreds or thousands of solar masses. Over billions of years, these initial seeds grew by devouring nearby gas and dust and merging with other black holes during galactic collisions, an evolutionary saga of accretion and amalgamation culminating in the supermassive entities we observe today. Another compelling hypothesis connects supermassive black holes to the first generation of stars, the elusive population 3 stars. These ancient stars, far larger and shorter-lived than stars forming today, could have collapsed into black holes of hundreds of solar masses. From these cosmic remnants, growth continued through the same relentless processes of accretion and mergers, sculpting the gargantuan black holes anchoring galaxies. Yet another idea invokes the collapse of dense clusters of stars under their own gravity, merging into a single massive black hole. Though this pathway holds less consensus, it remains a potential piece in the complex puzzle of supermassive black hole genesis. Despite these varying theories, one truth remains clear. Supermassive black holes are products of a dynamic cosmic dance, a grand interplay of gravity, gas dynamics, stellar evolution, and galactic mergers. Over cosmic timescales, complexity accumulates, weaving the intricate structures that define our universe. These colossal entities are not mere cosmic oddities, but pivotal anchors within galaxies, holding clues to the cosmos's evolutionary history. Understanding their formation illuminates not only their nature, but also the broader mechanisms shaping the universe itself, linking the microcosm of quantum gravity with the macrocosm of cosmic structure. And through this cosmic narrative, dark matter and energy shaping galaxies, singularities bending space and time, supermassive black holes growing from primordial seeds, the universe reveals a story of endless wonder and profound mystery. The pursuit to understand these phenomena is a journey into the deepest realms of physics, challenging humanity's knowledge and expanding the frontier of what is possible to comprehend. Each discovery draws us closer to the ultimate question: what is the true nature of the universe? And how does its grand design reflect the unseen forces that govern all existence? But also on the formation and evolution of galaxies and the universe itself, neutron stars stand as cosmic beacons, revealing secrets of nature under conditions so extreme they challenge the very limits of human understanding. These dense remnants of massive stars collapsed to unimaginable compactness serve as extraordinary laboratories where the fundamental laws of physics are put to the ultimate test, conditions that cannot be replicated in any terrestrial experiment. Imagine a sphere roughly the size of a city, yet packing the mass of our entire sun within it. This intense concentration of matter creates densities and gravitational fields so powerful that they bend and warp space-time itself, fulfilling the bold predictions made by Einstein's theory of general relativity. Observing neutron stars, especially pulsars, rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses, scientists probe the extreme gravity regime. Pulsars allow physicists to explore and verify general relativity's predictions when gravity is incredibly strong, sharpening and extending our grasp of how gravity truly operates in the universe. Inside these extraordinary stellar remnants lies a realm even more mysterious. The matter crushed to ultra-high densities forms what physicists call nuclear pasta, a strange and exotic state of matter named for its bizarre shapes, reminiscent of spaghetti, lasagna, and other Italian dishes. This nuclear pasta represents a fleeting phase just before matter collapses further into a black hole's singularity, providing a rare window into how nuclear matter behaves under pressures and densities far beyond anything achievable on Earth. In this way, neutron stars offer vital clues into the nature of nuclear forces, the fundamental strong interactions that hold atomic nuclei together, pushing the boundaries of nuclear physics and shedding light on how matter organizes itself when squeezed to the brink. Adding to the complexity, some neutron stars boast magnetic fields billions or even trillions of times stronger than the most powerful magnets humans have ever made. These magnetars, as they are known, turn the stars into natural laboratories for electromagnetism under conditions vastly exceeding those of terrestrial science. The titanic magnetic forces at play can trigger cataclysmic phenomena, starquakes that ripple through the crust of the star and giant flares releasing enormous bursts of energy, allowing researchers to study plasma physics and magnetohydrodynamics in environments impossible to recreate on Earth. But the fascination with neutron stars does not stop there. When neutron stars exist in binary systems, locked in close orbits with another neutron star or even a black hole, their dramatic mergers send ripples through the fabric of space-time itself. These ripples, known as gravitational waves, were predicted by Einstein, but only recently detected with remarkable precision by observatories like LIGO and Virgo. The study of these waves has opened a new era of astronomy, providing direct insights into the most violent cosmic collisions and confirming fundamental aspects of general relativity. These cosmic events allow physicists to peer into matter at nuclear densities and unravel mysteries that can connect gravity, nuclear physics, and quantum theory, thereby offering a unified perspective on the universe's most enigmatic forces. In essence, neutron stars serve as a cornerstone in modern physics, bridging diverse fields from gravitational theory and nuclear science to electromagnetism and quantum mechanics. Their study deepens our quest to comprehend the fundamental laws that govern the cosmos, making them indispensable to our understanding of the universe's fabric. Turning now to the black hole information paradox, a profound riddle at the crossroads of quantum mechanics and general relativity. This paradox was thrust into the spotlight by Stephen Hawking in the 1970s when he proposed that black holes are not entirely black. Instead, due to quantum effects occurring near their event horizons, the boundaries beyond which nothing can return, black holes emit a faint radiation now known as Hawking radiation. This groundbreaking discovery upended traditional views, suggesting black holes can slowly evaporate over time, losing mass until they potentially vanish entirely. This evaporation leads to a perplexing question. What happens to the information about all the matter and energy that fell into the black hole? According to the fundamental principles of quantum mechanics, information about a system's physical state can never be destroyed. It may transform or become highly scrambled, but it is always conserved. Yet, if a black hole disappears completely through evaporation, taking all the matter and energy with it, it appears that the detailed information about the stuff that fell in would be lost forever. This notion clashes head-on with quantum theory and thus presents a paradox, a tension that has challenged physicists for decades. The information paradox is far more than a theoretical curiosity. It strikes at the very foundations of physics and our understanding of reality. It highlights the incompatibility between our two most successful yet seemingly irreconcilable frameworks: quantum mechanics, which governs the microscopic realm, and general relativity, which governs the cosmic scale and gravity. Resolving this paradox is pivotal for constructing a coherent, unified theory of quantum gravity, one that harmoniously blends the quantum and classical descriptions of the universe and unveils the true nature of space-time and matter. Over the years, numerous theories have been proposed to resolve this paradox. Some suggest that information is somehow encoded in the subtle correlations of Hawking radiation itself, escaping the black hole as it evaporates. Others propose that information could leak out into alternate or parallel universes, circumventing loss in our own. Another radical idea is the concept of a firewall at the event horizon, a searing barrier that would obliterate incoming information, though this idea raises further troubling questions about the nature of black holes and space-time continuity. Despite these theories, the paradox remains an active focus of intense research, driving new advances in theoretical physics and deepening our understanding of black holes, quantum theory, and the ultimate quest for a theory of everything. Black holes themselves are some of the most enigmatic and fascinating objects in the universe. These gravitational wells are so intense that not even light can escape, making them perfect natural laboratories for testing the limits of physics. The discovery of Hawking radiation transformed black holes from inert cosmic sinks into dynamic quantum objects that emit radiation and lose mass. This insight has revealed that black holes could hold the keys to unifying quantum mechanics and gravity, two pillars of modern physics that remain stubbornly disconnected. Hawking radiation, predicted in 1974 by Stephen Hawking, implies that black holes are not completely black, but emit a faint glow due to quantum processes near their horizons. This revelation challenges our previous notions and forces us to rethink how information, matter, and energy behave at the edge of these cosmic abysses. The consequences ripple through many areas of physics, influencing how we understand entropy, information theory, and the fundamental structure of spacetime itself. Thus, the study of neutron stars and black holes not only expands our knowledge of the cosmos, but also probes the deepest questions about reality. These extraordinary celestial phenomena, where gravity, quantum mechanics, and nuclear physics intersect, remain at the forefront of scientific exploration. They embody the quest for knowledge about the universe's origin, evolution, and ultimate fate, revealing how nature's most extreme environments illuminate the path toward a unified understanding of the laws that govern all existence. But black holes emit radiation due to quantum effects near their event horizon, a phenomenon that fundamentally challenges our classical understanding of these cosmic giants. This radiation, often referred to as Hawking radiation, implies that black holes are not eternal. They gradually lose mass over time through this radiation, eventually evaporating and dissolving completely. This revelation was revolutionary because it represented a rare convergence of two foundational but traditionally incompatible pillars of modern physics: quantum mechanics, which governs the subatomic realm, and general relativity, which describes the gravitational fabric of spacetime on a cosmic scale. Further exploration into the quantum nature of black holes has led to the groundbreaking formulation of the holographic principle. This principle posits that the entire informational content of all the matter swallowed by a black hole could be encoded on its two-dimensional event horizon, rather than within its three-dimensional volume. Such a radical concept hints at a deeper and more fundamental understanding of space and time, suggesting that our perceived three-dimensional universe might itself emerge from two-dimensional information patterns encoded on cosmic boundaries. This challenges and potentially expands the conventional framework through which quantum mechanics is understood, blurring the line between geometry and information. Investigating black holes has also intensified the quest for a unified theory of quantum gravity, which seeks to seamlessly combine the inherently probabilistic nature of quantum mechanics with the smooth, continuous geometry of spacetime described by general relativity. Black holes serve as natural laboratories, extreme environments where the most intense gravitational fields could unveil new quantum phenomena hidden from view under less extreme conditions. Through these cosmic crucibles, physicists hope to unlock behaviors and interactions that transcend current theories, shedding light on the universe's most profound mysteries. Thus, black holes not only challenge our comprehension of the cosmos, but also provide a unique pathway to probe the deepest aspects of quantum mechanics. They push the boundaries of human knowledge, illuminating the path toward a more complete and fundamental theory of the universe's workings, one that integrates gravity with quantum principles. Magnetars represent another extraordinary astrophysical phenomenon, a rare and extreme variant of neutron stars characterized by their incredibly intense magnetic fields, among the strongest known in the universe, exceeding Earth's magnetic field by over a quadrillion times. These magnetic fields are so extraordinarily powerful that they can distort atomic structures themselves, stretching atoms into elongated rod-like shapes. Born from the catastrophic supernova explosions of massive stars, magnetars inherit their colossal magnetic fields through the conservation of magnetic flux and angular momentum during the stellar collapse that forms the neutron star. The importance of magnetars lies in their unique physical properties and behaviors, which offer invaluable insights into a wide range of astrophysical and fundamental physics problems. For example, magnetars are linked to some of the universe's most energetic and mysterious phenomena, including soft gamma repeaters, SGRs, and anomalous X-ray pulsars, AXPs. These are believed to be manifestations of magnetars emitting intense bursts and flares of gamma rays and X-rays. The energy released during these flares can temporarily outshine entire galaxies, and even from across the vast distances of the Milky Way, they have measurable effects on Earth's upper atmosphere. Studying magnetars deepens our understanding of neutron star physics, especially how matter behaves under the influence of extreme magnetic fields. This knowledge enriches our comprehension of stellar evolution, the final stages of massive stars, and the behavior of superdense matter under conditions that cannot be replicated in terrestrial laboratories. Moreover, magnetars serve as unique astrophysical laboratories for examining magnetohydrodynamics, the physics governing the dynamics of magnetized fluids, and the extraordinary effects of ultra-strong magnetic fields. The extreme magnetic environments surrounding magnetars also have profound implications for fundamental physics, particularly the study of quantum electrodynamics, QED. QED describes the interactions between light, photons, and matter, and in the presence of such formidable magnetic fields, magnetars provide a rare cosmic setting where exotic QED processes may occur. These processes offer a direct window into the nature of the quantum vacuum and the interactions between photons and magnetic fields, enabling tests of physical theories in regimes otherwise inaccessible. Black holes, meanwhile, remain one of the most compelling cosmic laboratories for testing the predictions of Einstein's general theory of relativity, which interprets gravity as the curvature of spacetime induced by mass and energy. The extreme gravitational conditions near black holes warp spacetime to an extraordinary degree, offering unique opportunities to observe and measure relativistic effects that cannot be replicated with less massive or less dense objects. One of the crucial ways black holes test general relativity is through the observation of their event horizons and the adjacent photon sphere. According to relativity, light passing close to a black hole should bend due to spacetime curvature, an effect known as gravitational lensing. This phenomenon has been observed and matches Einstein's predictions with remarkable precision. Another important test comes from monitoring the orbits of stars around supermassive black holes, such as Sagittarius A at the center of the Milky Way. The intricate dance of these stars, their orbital shapes, velocities, and subtle precessions align perfectly with the theoretical forecasts derived from general relativity. The detection of gravitational waves has opened an entirely new avenue for testing relativity. These waves are ripples in the fabric of spacetime produced by some of the universe's most violent events, like the mergers of black holes. The observed properties of gravitational waves, including their speed, frequency, and attenuation over distance, match the predictions of general relativity with astounding fidelity, providing powerful evidence in support of Einstein's framework. Additionally, the groundbreaking imaging of black holes by the Event Horizon Telescope (EHT) project represents a monumental achievement in astrophysics and a profound test of relativity. The images of the black hole shadow and the bright ring of light around the supermassive black hole in the galaxy M87 conform closely to theoretical predictions, offering a direct visual confirmation of concepts once thought purely theoretical. Together, these investigations into black holes and magnetars open windows into the extreme realms of the universe. They bridge the cosmic and quantum, the large and the small, and provide an unprecedented laboratory to push the limits of physics. The ongoing study of these enigmatic celestial objects promises not only to deepen our understanding of fundamental forces and particles, but also to inspire new theories that could revolutionize our conception of reality itself. And this visual evidence powerfully reinforces the theory's remarkable precision in describing the intricate dance between light and matter when caught in the grip of extreme gravitational forces. Each of these vivid examples throws a spotlight on black holes as the universe's own natural laboratories, testing grounds where the very edges of general relativity are pushed and probed. By scrutinizing these enigmatic cosmic phenomena, scientists delve deeper into the fundamental laws that govern the fabric of the cosmos itself, potentially paving the way toward revolutionary new physics that stretch far beyond the boundaries of our current theoretical understanding. And since the first monumental detection in 2015, the field of gravitational wave astronomy has exploded with rapid, transformative advancements, continually unveiling new, breathtaking insights into the universe's most profound mysteries. Among these breakthroughs, several stand out for their profound implications and groundbreaking contributions to our understanding of cosmic evolution and structure. One of the most landmark discoveries is the detection of gravitational waves emanating from the cataclysmic merger of neutron stars. The 2017 event marked a watershed moment in astrophysics, for it was the first time scientists observed not only the elusive ripples in spacetime, but also a symphony of electromagnetic signals, gamma-ray bursts followed by a cascade of visible infrared and X-ray emissions, each wave of light revealing fresh layers of the cosmic story. This watershed event has heralded the dawn of multi-messenger astronomy, a revolutionary approach that combines different cosmic signals into a comprehensive narrative, enriching scientists' understanding of these violent and transformative events. And from this neutron star collision, new revelations emerged about the cosmic origin of heavy elements such as gold and platinum. The evidence suggested that these dazzling metals cherished on Earth owe their existence largely to such cosmic cataclysms, reshaping our understanding of the cosmic alchemy that produces the building blocks of planets and life. More recently, the frontier has expanded with the groundbreaking identification of gravitational waves from what appears to be a black hole colliding with a neutron star, an extraordinary event never directly witnessed before. This opens an unprecedented window into matter under the most extreme conditions imaginable, offering a rare testbed for general relativity's predictions in uncharted regimes and challenging scientists to refine and rethink long-held theories. And the collaborations between LIGO and Virgo observatories have pushed the limits of discovery even further. Their observations have revealed black holes of staggering variety, ranging from the smallest to the most massive black holes ever detected through gravitational waves. Some of these black holes challenge existing stellar evolution models, particularly those found in the mysterious mass gap between neutron stars and black holes. Others hint at a population of black holes grown through hierarchical merging, cosmic giants forged by the collision of smaller black holes over eons, illustrating a complex and dynamic black hole ecosystem. And with every leap in the sensitivity of gravitational wave detectors, humanity's gaze extends deeper into the universe, capturing signals from ever more distant and diverse sources. Among these potential discoveries are continuous gravitational waves emitted by rapidly rotating neutron stars, offering tantalizing possibilities for probing the inner structure and mysterious behaviors of these dense stellar remnants in unprecedented detail. Each fresh observation not only puts general relativity's predictions to the ultimate test, but also provides invaluable data that illuminate the life cycles of stars, the intricate processes behind the formation of heavy elements, the mysterious structure of neutron stars, and the grand evolutionary history of galaxies themselves. In a relatively short time, gravitational wave astronomy has transformed into an indispensable tool, an explorer's compass guiding us through the universe's most violent and energetic episodes, relentlessly pushing the boundaries of human knowledge. And beyond these empirical triumphs lie the tantalizing theoretical landscapes of wormholes and white holes, concepts born directly from the equations of Albert Einstein's field equations within the framework of general relativity. These notions, while deeply rooted in rigorous physics, venture boldly into the realm of cosmic speculation, challenging and expanding our very comprehension of spacetime's architecture. Wormholes, also known as Einstein-Rosen bridges, are envisioned as hypothetical tunnels weaving through spacetime's fabric, potentially creating shortcuts for travelers journeying across vast cosmic distances. Predicted by general relativity's mathematical framework, these structures tantalize the imagination with possibilities of faster-than-light travel and shortcuts between distant regions of the universe, though their existence remains firmly in the domain of theory and mathematical elegance rather than observation. And white holes, the speculative cosmic cousins of black holes, represent hypothetical regions where matter and energy could emerge instead of disappearing. Enigmatic phenomena that, if proven, could profoundly rewrite our understanding of the universe's beginnings, endings, and the flow of information across spacetime. Thus, from the very tangible discoveries in gravitational waves to the far-reaching theoretical horizons of wormholes and white holes, modern astrophysics weaves a breathtaking tapestry, one that pushes the frontiers of human knowledge and inspires awe at the mysterious grandeur of the cosmos, but have yet to be observed. Wormholes remain one of the most tantalizing enigmas of modern theoretical physics. These hypothetical tunnels through the fabric of spacetime could, in principle, bridge vast cosmic distances instantaneously, transforming science fiction dreams into potential realities. Imagine traversing the universe from one star system to another in the blink of an eye, or even stepping across epochs to witness the past or future firsthand. Yet the very nature of these exotic passages poses monumental challenges. According to our current understanding, the laws of physics conspire against the stability of wormholes. If they exist at all, these cosmic shortcuts would likely collapse almost instantly, denying any matter or information the chance to journey through. To prevent such a rapid implosion, theoretical models require an unusual kind of substance known as exotic matter, characterized by negative energy density, capable of holding the wormhole's throat open. But this exotic matter remains elusive, and its existence is purely speculative, making the prospect of traversable wormholes still far beyond our experimental reach. White holes, by contrast, represent the mirror image of black holes in the cosmic ledger. Whereas black holes are notorious for their insatiable appetite, swallowing everything that ventures too close and imprisoning it beyond their event horizons, white holes repel. These hypothetical entities would expel matter and energy, creating regions of spacetime that nothing can enter but only escape from. The mathematical solutions to Einstein's field equations that describe black holes also allow for these white holes, but despite their theoretical consistency, no white hole has ever been detected or observed in the universe. Some theories suggest white holes might be the exit points of wormholes or the outflow regions connected to black holes, possibly ejecting matter in a way that challenges our understanding of thermodynamics and the arrow of time. Nevertheless, the existence and nature of white holes remain firmly in the realm of speculation without empirical evidence to substantiate their reality. Both wormholes and white holes have fascinated not only scientists, but storytellers and visionaries alike. They symbolize the unknown boundaries of our universe and challenge the foundations of physics. In science fiction, they open gateways to extraordinary adventures, while in theoretical physics, they serve as crucibles for testing the limits of Einstein's theory of general relativity. By studying these concepts, researchers push the envelope of human knowledge, seeking to unravel the mysteries of space-time, gravity, and the cosmos itself. Could wormholes someday be harnessed for interstellar travel? Could white holes illuminate new principles of energy and entropy? These questions propel the frontier of modern physics, inspiring innovative theories and driving the relentless quest for empirical proof. Recent advances in astrophysics have shifted the focus from purely theoretical constructs to observable phenomena, especially through the study of black holes. The detection of gravitational waves, a ripple in the fabric of spacetime predicted by Albert Einstein over a century ago, has revolutionized our understanding of these cosmic titans. The first confirmed observation of gravitational waves in 2015, produced by the collision of two massive black holes, unveiled a hidden dance in the universe previously invisible to human eyes. These cataclysmic mergers release staggering amounts of energy, warping space-time itself, and sending waves that ripple across the cosmos. Yet, the origin stories of these massive black hole pairs remain enigmatic. How do such colossal objects, sometimes many times the mass of our sun, come to orbit each other in such a tight cosmic embrace before their eventual violent union? The answers lie deep within the processes of galactic evolution, the life cycle of stars, and in the dynamic environments where these black holes are born and grow. Beyond the astrophysical intrigue, these gravitational wave events have profound implications for cosmology. The merging black holes act as cosmic laboratories, helping refine our measurements of the universe's expansion rate, a fundamental parameter that remains a subject of debate and investigation. Moreover, by studying these mergers, scientists glean insights into the elusive distribution of both visible matter and the enigmatic dark matter that dominates cosmic mass. As detection technology continues to advance, each observed black hole merger adds a new piece to the vast cosmic puzzle, enriching our understanding while deepening the mysteries that define the universe's most enigmatic phenomena. The concept of a multiverse, where our known universe is but one bubble in a potentially infinite sea of alternate universes, each governed by its own unique laws of physics, challenges the very notion of cosmic singularity. This mind-bending idea has captivated physicists and cosmologists alike, offering radical new perspectives on the origins and ultimate fate of everything we know. One of the intriguing hints supporting this idea comes from subtle irregularities in the cosmic microwave background, CMB, the faint afterglow radiation left over from the Big Bang that permeates the cosmos. Scientists have detected cold spots in the CMB that defy straightforward explanations within the physics of our own universe. These anomalies might signify gravitational effects exerted by other universes beyond our observable horizon, tugging at the fabric of our cosmos in ways we have yet to fully comprehend. Furthermore, the theory of cosmic inflation, the rapid exponential expansion of the universe in its earliest moments, naturally leads to the formation of a multiverse. According to this theory, different regions of space could inflate at different rates or stop inflating at different times, creating a patchwork quilt of universes with varying physical constants and laws. This grand vision reshapes our understanding of reality itself, suggesting that our universe's laws are but one possibility among an infinite tapestry of cosmic diversity. Thus, from the theoretical realms of wormholes and white holes to the tangible echoes of black hole mergers and the tantalizing prospects of a multiverse, modern physics is engaged in an epic quest. This quest not only seeks to explain the unseen depths of space-time and gravity, but also to unlock new chapters in the story of existence. Each discovery fuels our imagination and expands the boundaries of what is scientifically possible, driving humanity ever closer to understanding the full grandeur and complexity of the cosmos. And so, this theory unfolds a vision of the cosmos that is as vast and enigmatic as the night sky itself. It suggests that different regions of space might cease their rapid inflation at varying times, giving birth to separate, self-contained bubble universes. These bubbles could float alongside one another, each a universe unto itself, with its own laws, constants, and histories, nestled within an overarching multiverse, a grand cosmic mosaic far beyond what our senses can directly perceive. Yet, despite the profound implications of this idea, direct evidence remains stubbornly elusive, hidden at the edge of scientific reach and human imagination. But the story does not end with mere speculation. Scientists continue to chase clues and weave observations into a tapestry that hints at something greater, a multiverse where our universe is but a single thread woven into an infinite expanse. Detecting other universes might sound like a tale spun from the pages of science fiction, yet the quest demands the sharpest minds and the most advanced instruments humanity has ever devised. It challenges our deepest understanding of physics and the very fabric of reality, compelling us to peer into the cosmic horizon itself. One of the most promising avenues in this search lies in the cosmic microwave background radiation, or CMB, the faint afterglow of the Big Bang. This relic radiation blankets the entire sky, a whisper from the infancy of our universe. Scientists scrutinize this ancient light for subtle irregularities, patterns that could betray interactions with other universes. If a neighboring bubble universe were to collide with ours, such a cataclysmic encounter might leave a distinctive scar, a bruised imprint on the CMB. These marks, if found, could provide an extraordinary window into realms beyond our own, detected by instruments so sensitive that they measure temperature fluctuations as small as a millionth of a degree. Moreover, gravitational waves, ripples in the very fabric of space-time predicted by Einstein and first directly observed in recent years, offer another potential key to unlocking the multiverse. These waves emanate from cataclysmic cosmic events like colliding black holes or neutron stars, but some theorists propose that unique gravitational signatures could emerge from interactions with other universes, vibrations of spacetime that cannot be explained by any event within our own. Observatories like LIGO, the Laser Interferometer Gravitational Wave Observatory, are on the lookout for these subtle signals, pushing the boundaries of technology and precision. And then there is dark matter, the elusive substance that neither emits nor absorbs light, yet exerts a gravitational pull that shapes galaxies in the large-scale structure of the cosmos. Some physicists theorize that anomalies in the distribution of dark matter could hint at the gravitational influence of parallel universes, their hidden presence tugging gently on our own cosmos. Although such ideas remain speculative, they open new pathways in the ongoing journey to understand the unseen forces at play. Yet, beyond the multiverse and bubble universes, the very nature of dimensions themselves demands attention. Theoretical physics ventures into realms that defy everyday experience, proposing extra dimensions beyond the familiar 3 of space and 1 of time. Among these theories, string theory stands as a towering edifice, a radical idea that the fundamental constituents of reality are not point-like particles, but minuscule, vibrating strings. These strings oscillate at different frequencies, giving rise to the particles and forces that shape our universe, much like the strings of a violin produce a symphony of notes. String theory's elegant mathematics requires more than the 4 dimensions we perceive. It predicts the existence of up to 11 dimensions. These extra dimensions, however, are not spread out like the dimensions we know, but are tightly curled up, compactified into shapes so small they elude direct detection by any current instrument or human sense. The challenge of probing these dimensions stretches the limits of physics and technology, inspiring novel experimental approaches. In parallel, the reconciliation of quantum mechanics, the laws governing the smallest scales, and general relativity, the theory describing the large-scale structure of spacetime, has long confounded physicists. Theories like supergravity and superstring theory attempt this unification, implying that additional dimensions are essential for the mathematical consistency of the laws that govern the cosmos. They also offer potential explanations for puzzles, such as why gravity is so much weaker compared to the other fundamental forces, possibly due to its leaking into hidden dimensions. These explorations are not mere abstract musings. They strive to answer profound questions about the nature of reality itself. What lies beyond our observable universe? How does the cosmos operate at its most fundamental level? What unseen structures underpin the universe's astonishing complexity? Detecting extra dimensions is a monumental task. These dimensions are theorized to exist at scales on the order of the Planck length, approximately 10⁻35 meters, a scale billions of times smaller than an atom's nucleus. To glimpse evidence of these dimensions, physicists turn to the highest energy experiments humanity can conduct. Particle colliders, such as the Large Hadron Collider, accelerate protons to near light speeds and smash them together, recreating conditions that prevailed moments after the Big Bang. Within these violent collisions, some theories suggest that particles might temporarily vanish into extra dimensions, slipping beyond our observable 4-dimensional spacetime. Although they must return almost instantaneously, their brief escape could leave subtle, yet measurable traces, missing energy or momentum, that hint at the presence of hidden dimensions. These signs would be faint and difficult to distinguish from other processes, but they represent one of the few direct experimental windows into realms beyond our senses. Beyond particle accelerators, physicists consider other experimental possibilities: miniature black holes that might form and evaporate in these collisions, modifications in the strength of gravity at short distances, or exotic particles predicted by these theories. Each possibility is a potential beacon, illuminating pathways toward a deeper understanding. And so this grand theoretical edifice stretches from the birth of the universe in the Big Bang to the vibrating strings at the heart of matter, from the ghostly afterglow of cosmic radiation to the ripples of gravitational waves. It calls on humanity to expand its technological prowess and intellectual reach to uncover secrets hidden in the smallest scales and the farthest corners of space. The journey to uncover the multiverse and the extra dimensions is more than a scientific endeavor. It is a profound exploration of existence itself, a quest to reveal the ultimate nature of reality and our place within it. This tale of cosmic investigation weaves together the cutting edges of physics, cosmology, and technology, challenging us to imagine beyond the known and to question the very fabric of the universe. It is a testament to human curiosity and perseverance, a narrative of discovery that continues to unfold with every experiment, every observation, and every bold theoretical leap. But detectable signals, such as an unexpected energy deficit, open a new frontier in the search for extra dimensions. Another method lies in probing the subtle gravitational effects that extra dimensions might impose on scales just above the quantum level. If gravity, unlike the other fundamental forces, can seep or leak into dimensions beyond the familiar three spatial ones, then precise experiments designed to measure gravitational forces at extremely short ranges could reveal subtle deviations from Newton's long-established law of universal gravitation. These deviations, if detected, would be like ripples in the fabric of our known reality, hinting at hidden dimensions woven beneath the surface of the cosmos. Furthermore, astrophysical observations provide another tantalizing window into the possible presence of extra dimensions. Imagine, for a moment, tiny black holes forged in the earliest moments of the universe, shortly after the Big Bang. Their behavior, the way they form, evolve, and eventually evaporate through Hawking radiation, might be significantly influenced by the structure of extra dimensions. This influence could leave telltale signatures in the cosmic data we gather today. These might emerge in the patterns of high-energy cosmic rays bombarding Earth, or in the gravitational waves rippling through space-time. Subtle whispers from the dawn of creation. Although direct detection of extra dimensions remains elusive, these inventive approaches exemplify the daring ingenuity of physicists pushing the boundaries of our understanding and technology to probe the very foundations of reality. If the concept of a multiverse were ever to be confirmed, it would revolutionize our understanding of existence itself. It would shift the narrative from a single, solitary universe to an almost unimaginable vastness filled with countless distinct universes, each potentially governed by its own unique set of physical laws. This revelation would shatter the assumption that the constants and laws of physics we observe are universal truths, instead revealing them as local phenomena, rules that apply only within the confines of our particular universe. The confirmation of a multiverse would also have profound implications for the nature of scientific explanation and prediction. It could provide a compelling solution to the long-standing fine-tuning problem, where certain fundamental constants appear exquisitely balanced to allow the emergence of life. In a multiverse scenario, these conditions might not be a cosmic coincidence, but rather the inevitable outcome of a vast cosmic lottery, with countless universes possessing different parameters, and ours simply being one where life is possible. This perspective transforms the philosophical underpinnings of cosmology and physics, suggesting a far more complex and layered reality than previously imagined. On a deeper philosophical level, the existence of a multiverse could challenge our most basic notions of determinism and causality. Instead of a single linear outcome for any event, multiple outcomes could all be realized, each unfolding in different universes. This forces us to reconsider the nature of time, causality, and even free will, reshaping our conception of reality in fundamental ways. It may also compel a radical reevaluation of the universe's origin and ultimate fate, proposing not a singular cosmic beginning, but an eternal, self-replicating inflationary process, endlessly birthing new universes in a ceaseless cosmic bloom. Existentially, the idea of a multiverse confronts us with the humbling possibility that our universe, and by extension our existence, might not be unique or central. Yet paradoxically, it could also broaden our sense of wonder and curiosity, revealing a far grander and more diverse cosmic landscape than ever imagined. This expanded cosmic panorama could inspire new questions, new explorations, and a renewed sense of awe at the vastness of existence. Within the framework of multiverse theory, it is not just possible, but probable, that the physics governing other universes could differ radically from our own. Each universe might spring forth with a unique set of physical laws and constants. The fundamental forces, gravitational, electromagnetic, strong nuclear, and weak nuclear, that shape the fabric of our universe might behave differently elsewhere. The masses of elementary particles could vary wildly, resulting in chemistry and matter forms utterly alien to us. In universes where gravity is significantly stronger or weaker, the formation of stars, galaxies, and potentially life itself might be altered beyond recognition. Changes in electromagnetic force strength could lead to novel chemical interactions, giving rise to forms of complexity unimaginable within our physical framework. This vast diversity challenges theoretical physics to redefine what is fundamentally possible, stretching our concepts beyond familiar boundaries. It reinforces the notion that our universe, with its finely tuned laws and constants that allowed life to emerge, might be just one of an infinite ensemble, each with its own unique story, structure, and potential. The notion of a multiverse also deeply influences philosophical and ethical thought, extending the horizon of inquiry far beyond the confines of our own universe. Philosophically, it confronts the anthropocentric view that human beings occupy a special, central place in the cosmos. Instead, the multiverse suggests our universe might be one among countless others, possibly teeming with diverse forms of life and intelligence. This perspective invites a profound reassessment of our significance, life, urging humility and an expanded curiosity toward existence itself. From an ethical standpoint, the multiverse raises challenging questions about our moral responsibilities. If sentient beings exist across different universes, what obligations do we have toward them? How do we weigh the value of lives that may unfold under entirely different physical realities? These considerations complicate traditional ethical frameworks, pushing us to think in new dimensions, both literally and figuratively, about the scope of moral concern and the nature of life itself. Thus, from the tiniest ripples of gravity to the sprawling infinity of possible universes, the pursuit of extra dimensions and the multiverse concept push the frontier of human knowledge and imagination. These ideas beckon us to look beyond the familiar, to question our assumptions, and to embrace the profound mystery of a reality far more vast, intricate, and wondrous than we have ever dared to dream. But to hypothetical beings in other universes, especially if our actions, experiments in physics, for example, that carry the potential for cross-universal repercussions, might ripple through and alter the very fabric of these alternate realities. Moreover, the multiverse theory doesn't merely rest as a speculative notion in cosmology. It wields profound influence over philosophical discourse, particularly on determinism and free will. If every conceivable outcome of every event unfolds in some corner of the multiverse, we are compelled to revisit our deepest understandings of choice, fate, and personal agency. Within this vast expanse of infinite realities, every version of our lives, every decision taken, every path not chosen, is played out somewhere, and this challenges the very core of how we conceive individuality and consequence. Finally, the multiverse concept thrusts us into complex ethical debates, especially regarding humanity's dedication of resources towards scientific exploration. It confronts us with a profound question. How much effort and funding should be allocated to the pursuit of theories that, while potentially revolutionary, stretch the limits of empirical verifiability? This ethical balancing act requires us to weigh the thirst for knowledge itself against the tangible benefits such discoveries might yield for our own universe. In essence, the multiverse theory expands not only the scientific canvas, but also the philosophical and ethical terrain we must navigate, pushing us to confront fundamental questions about reality, existence, and our place within this cosmic framework, questions that may forever remain without definitive answers. The quest for evidence supporting the multiverse presents scientists with formidable challenges. Rooted in theoretical complexity and compounded by practical limitations of contemporary scientific methodology, the hurdles are daunting. A primary obstacle is the inherent unobservability of other universes. By their very definition, these alternate realms lie beyond the bounds of our observable universe, making direct detection or interaction all but impossible with our current technology. This barrier leads to a significant problem for scientific validation: falsifiability. A cornerstone of the scientific method demands that for a theory to be considered valid, there must be a conceivable way to disprove it. Yet, if other universes remain forever beyond observation and measurement, constructing a test capable of falsifying the multiverse theory becomes an almost insurmountable challenge. Further complicating this pursuit is our reliance on indirect evidence, particularly from interpretations of cosmological data such as the cosmic microwave background radiation or the distribution of dark matter. Anomalies or unexplained phenomena within these datasets might hint at influences from other universes, but equally, they could reveal gaps in our understanding of our own universe's physics. This ambiguity makes it extremely difficult to attribute any observed phenomena definitively to the presence of a multiverse. Add to this the speculative nature of the theoretical frameworks underpinning the multiverse, such as string theory and inflationary cosmology, which themselves are subjects of ongoing debate and refinement within the scientific community. These evolving theories further muddy the waters, complicating the path toward concrete evidence. The sheer scale and ambition of experiments or observations needed to confirm the multiverse is staggering. The technological advancements and resources required likely exceed current human capabilities. Progress demands not only innovations in physics and astronomy, but also conceptual breakthroughs in how we frame and investigate the fundamental nature of reality. Despite these monumental obstacles, the search for evidence continues to inspire scientists, driving exploration into the unknown, pushing the boundaries of cosmic knowledge. Several possible observable effects might indirectly suggest the presence of other dimensions, even though these dimensions themselves may lie beyond direct detection due to their compact scale or the nature of their interaction with our observable universe. One such indicator concerns the behavior of gravity at extraordinarily small scales. Theories incorporating extra dimensions propose that gravity might deviate from its expected behavior at distances smaller than we can currently probe. If future technologies enable us to examine gravity at the Planck scale, approximately 10 to the minus 35 meters, any deviations from Newton's inverse square law could point toward the influence of these extra dimensions. Another tantalizing potential observable effect emerges from high-energy particle collisions, such as those at the Large Hadron Collider. Certain theoretical models predict that the threshold energy required to produce microblack holes might be significantly lower if extra spatial dimensions exist. If these miniature black holes were created and subsequently decayed within particle accelerators, their detection would provide indirect but powerful evidence for dimensions beyond the three spatial ones familiar to us. Similarly, the cosmic microwave background radiation, the afterglow of the Big Bang, might carry imprints of higher dimensions. Unexplained temperature fluctuations or polarization patterns within this radiation, unaccounted for by standard cosmological models, could reveal physics shaped by these additional spatial dimensions. Moreover, the discovery of particles or phenomena unexplained by the standard model of particle physics could hint at extra dimensions. Particles exhibiting unexpected masses or charges, or forces mediated by unknown carriers, might be manifestations of interactions with fields or particles connected to higher dimensional spaces. Confirming any of these effects requires exceptionally precise measurements and the development of novel physics theories, making the hunt for evidence of extra dimensions one of the most exciting and challenging frontiers in contemporary physics. The holographic principle presents a revolutionary and elegant bridge between gravity and quantum mechanics, connecting disparate fields and reshaping our understanding of space and information. At its core, the principle suggests that all information contained in a volume of space can be fully represented as encoded data on that volume's boundary. On a cosmic scale, This means our entire three-dimensional universe might be understood as a projection from two-dimensional information residing on its outer boundary, much like a hologram. Born out of attempts to reconcile general relativity, which governs the large-scale universe, with quantum mechanics, which describes the microcosm, the holographic principle emerged from research into the enigmatic nature of black holes. Physicists grappled with the paradox of whether information about particles falling into a black hole is lost forever, defying quantum laws. The holographic principle offered a resolution, proposing that such information is preserved, encoded on the event horizon, the boundary of the black hole, thereby safeguarding the fundamental tenets of physics. This principle extends far beyond black holes, suggesting a profound rethinking of how information, space, and reality intertwine at the deepest level. It hints at a universe where what we perceive as volume and depth may be a shadow of a more fundamental, two-dimensional informational structure. In this light, the holographic principle does not merely propose a new scientific idea, but challenges us to reconsider the very fabric of existence and the architecture of the cosmos itself. Together with theories of the multiverse and extra dimensions, it represents a bold step toward unifying the physics of the incredibly vast with that of the infinitesimally small, drawing us ever closer to a comprehensive understanding of reality that transcends traditional boundaries. But encoded on the event horizon of a black hole lies a secret that could revolutionize our understanding of the cosmos itself. When applied to the universe as a whole, the holographic principle unveils a paradigm-shifting vision of reality, one that challenges everything we think we know about space-time and gravity. In this breathtaking view, gravity is not a fundamental force, but rather a shadow cast by deeper, simpler flat universes encoded on the cosmological horizon, the boundary beyond which we cannot see or interact. This boundary acts like the ultimate cosmic screen, projecting the three-dimensional reality we inhabit from information stored in two dimensions. This startling concept ignites the profound possibility that our experience of reality, three-dimensional space, the inexorable pull of gravity, the relentless flow of time, may all emerge from complex information processes occurring at the universe's very edge. In other words, what we perceive as solid continuous existence is, at its core, a hologram, a cosmic illusion crafted from data inscribed on a distant, nearly invisible surface. Incorporating the holographic principle into cosmology opens up extraordinary new vistas in fundamental physics. It forces us to reconsider the nature of space and volume, not as fundamental entities, but as emergent phenomena arising from information processing at the smallest scales. This insight bridges one of the most daunting chasms in modern science, reconciling the seemingly incompatible worlds of quantum mechanics, the physics of the very small, and general relativity, the physics of gravity and the very large. Through this lens, theoretical physics embarks on a daring journey into uncharted territories, redefining the very fabric of reality and the laws that govern it. Exotic matter, on the other hand, occupies a realm as strange and mysterious as the holographic universe itself. Defined by its radical departure from the properties of conventional matter, exotic matter defies the everyday laws of physics. Its behaviors challenge our deepest intuitions about gravity and inertia, often involving negative mass or energy density, phenomena that invert the usual gravitational attraction and push the boundaries of what is physically plausible. Unlike the matter that composes stars, planets, and people, exotic matter does not naturally occur under normal conditions in our observable universe. Instead, it exists primarily as a theoretical concept with profound implications in advanced cosmology and theoretical physics. One of the most tantalizing contexts for exotic matter lies in the science fiction-like hypotheses surrounding wormholes and warp drives. Wormholes, the hypothetical shortcuts connecting distant points in spacetime, demand the presence of exotic matter to exist. This exotic matter would provide the negative energy density necessary to counteract gravitational collapse, stabilizing these cosmic tunnels and keeping them open for potential travel. Without it, wormholes would pinch off and vanish as quickly as they appeared. Similarly, the speculative Alcubierre warp drive concept, a theoretical model for faster-than-light space travel, relies on a bubble of exotic matter. This bubble would compress space in front of a spacecraft and expand it behind, effectively warping space-time itself to propel the vessel faster than light without violating Einstein's cosmic speed limit. Though deeply theoretical and currently beyond our engineering reach, such ideas fuel the dreams of interstellar exploration and challenge the boundaries between science and imagination. Within the quantum realm, the Casimir effect offers tantalizing experimental support for the strange properties of exotic matter. When two uncharged parallel metal plates are brought incredibly close together in a vacuum, they experience an attractive force, a direct result of negative pressure generated by quantum fluctuations in the space between them. This phenomenon illuminates the strange, invisible world of virtual particles, fleeting entities that pop in and out of existence, and the subtle, intricate behaviors of quantum fields. It hints at the deep and intricate nature of exotic matter and its possible reality in our universe. Beyond the cosmos and quantum experiments, exotic matter might also lurk in the extreme environments of neutron star cores or the intense conditions moments after the Big Bang, where conventional physics breaks down and new unknown forms of matter may arise. Despite its crucial role in theoretical models, directly observing or producing exotic matter remains a distant goal, far beyond current technological capabilities. Its elusive nature keeps it squarely in the realm of theoretical physics, yet it remains vital for probing the limits of physical laws and exploring technologies that sound like pure science fiction. Exotic matter's hypothetical traits, negative mass and energy density, may hold the keys to breakthroughs in propulsion and space travel technologies, like the elusive warp drive popularized in science fiction stories and futuristic dreams. These concepts push humanity's imagination and scientific inquiry to new frontiers, opening doors to the possibility that what once seemed impossible might someday be within reach. The holographic principle and exotic matter together shape a cosmos where information, gravity, and matter weave an intricate, mysterious tapestry, inviting us to peer deeper into the universe's ultimate secrets and our place within its vast expanse. But grounded in the real laws of physics, the concept of faster-than-light travel takes shape not as pure science fiction, but as a daring theoretical framework that stretches the limits of our understanding of space-time itself. Imagine creating a bubble around a spacecraft, a region of warped space-time that moves independently from the space outside it. This bubble would allow the vessel inside to travel faster than light relative to the universe beyond its boundary, all without breaking the inviolable speed limit imposed by Einstein's theory of relativity. The most well-known model illustrating this idea is the Alcubierre warp drive. Proposed by physicist Miguel Alcubierre in 1994, it involves manipulating space-time by compressing it in front of the ship while expanding it behind. The ship itself would rest in a warp bubble, which remains flat and stable within, protecting passengers from the intense forces acting on the bubble's edges. The warp bubble effectively moves the spacecraft by contracting and expanding space-time around it, allowing it to traverse cosmic distances at speeds that, from an external observer's perspective, exceed that of light. The key to this extraordinary possibility lies in exotic matter, a hypothetical form of matter with negative energy density. This exotic matter would be crucial in generating the negative energy necessary to warp space-time in this unusual way. Unlike normal matter, which pulls on space-time, exotic matter would push or pull in ways that create a sort of space-time distortion. If harnessed or synthesized in sufficient quantities, it could be the cornerstone of humanity's first genuine faster-than-light propulsion system, enabling exploration of distant stars and galaxies within a human lifetime. However, this vision remains firmly in the realm of theoretical physics due to colossal practical challenges. Exotic matter itself remains a speculative concept without experimental confirmation. No known physical process or technology exists to create or stabilize exotic matter in quantities large enough to sustain a warp bubble. Even if exotic matter could be harnessed, the energy required to maintain a warp bubble would be astronomical, far beyond anything humanity can currently generate or control. Engineering a spacecraft capable of withstanding these extreme space-time manipulations while ensuring the safety of passengers compounds these difficulties exponentially. Despite these monumental obstacles, the allure of warp drives continues to inspire theoretical research, pushing the boundaries of our understanding of space-time, matter, and the ultimate possibilities of human space travel. The notion of warping space-time captivates scientists and dreamers alike, challenging the limits of what we consider feasible and opening new frontiers in fundamental physics. While the dream of warp travel presses forward, particle accelerators are playing an equally vital role in expanding our cosmic knowledge. These massive machines, such as the Large Hadron Collider, accelerate subatomic particles to near light speed and smash them together with tremendous energy. In these high-energy collisions, scientists recreate conditions akin to those in the universe's first fractions of a second after the Big Bang. Such experiments have led to groundbreaking discoveries, including the confirmation of the Standard Model of particle physics, a framework describing 3 of the 4 fundamental forces and all known elementary particles. One of the crowning achievements of particle accelerator experiments was the discovery of the Higgs boson in 2012, confirming how particles acquire mass and completing the Standard Model's picture. Yet, particle physics extends beyond confirming existing theories. It seeks new physics to explain phenomena that remain mysteries today. Researchers use these accelerators to search for supersymmetric particles, hypothesized counterparts that could fill gaps in our understanding and possibly account for dark matter, a mysterious substance composing roughly 85% of all matter in the universe, but invisible because it does not interact with light. Dark matter's gravitational effects shape the large-scale structure of the cosmos and influence galaxy formation, but direct detection remains elusive. Alongside dark matter, dark energy, a mysterious force driving the accelerating expansion of the universe, composes nearly 70% of the universe's energy content. These two components dominate the cosmos, yet their true natures remain among the most profound puzzles in modern science. The search for dark matter and dark energy intertwines with the limits imposed by fundamental physics. Quantum mechanics introduces inherent uncertainties, such as the Heisenberg uncertainty principle, which limits our ability to precisely measure a particle's position and momentum simultaneously. This principle reveals the universe's intrinsic fuzziness at the smallest scales, setting a boundary on how fully we can comprehend the quantum realm. On a cosmic scale, the speed of light imposes a horizon, the observable universe's edge. Light from beyond this cosmic boundary has not yet reached us since the Big Bang, meaning entire regions of the universe may forever lie beyond our observational reach. Within these inaccessible regions, unknown phenomena or even new physical laws might exist, hiding from human inquiry. As physics ventures deeper, the challenge of complexity grows. Some problems may be computationally unsolvable given current methods and technology. Theories also become increasingly abstract, making empirical verification difficult, pushing the philosophy of science to confront how we validate our models of reality. After all, our theories are human-made constructs, shaped by our cognitive capacities and biases, offering the best approximations of nature that our minds can conceive. Yet these limits are not barriers, but catalysts. They drive scientists to innovate, build more powerful tools, and devise ingenious experiments. The quest to understand the universe is relentless, spanning particle physics, cosmology, quantum gravity, and beyond. In this grand quest, concepts like loop quantum gravity emerge as tantalizing attempts to unify the disparate realms of quantum mechanics and general relativity. This theory proposes that space itself is composed of discrete, granular elements rather than a smooth continuum. Such a framework may reconcile the contradictions between gravity and quantum phenomena and reveal the fabric of the universe at its deepest level. As humanity probes these mysteries, powerful instruments like the Large Hadron Collider and space-based observatories advance our reach. They bring us closer to discovering the particles and forces that underpin reality, unveiling truths that could redefine our place in the cosmos. The pursuit of understanding dark matter and dark energy, the potential of exotic matter and warp drives, and the limits imposed by quantum and relativistic physics, together weave a tapestry of exploration and curiosity. Each discovery opens new horizons, transforming the once unimaginable into possibilities for the future. The universe is vast and mysterious, filled with wonders, both visible and hidden. Our journey to comprehend it is a story of daring ideas, relentless experimentation, and profound questions. Through this ongoing odyssey, science lights the way, guiding humanity ever deeper into the cosmic ocean, chasing the promise of knowledge and the dream of someday reaching the stars. But is composed of tiny discrete loops akin to the threads of a fabric. These loops are so minuscule that their size is measured on the Planck scale, which is about 100 million trillion times smaller than an atom. This groundbreaking approach suggests that space and time themselves are granular, and their apparent smoothness emerges only at larger scales observable by humans. Should loop quantum gravity hold true, it could dramatically transform our understanding of the cosmos, especially in conditions of extreme gravity such as those found inside black holes or during the universe's birth at the Big Bang. Unlike conventional theories that predict singularities, points where the equations of physics break down and our current understanding ceases to apply, loop quantum gravity proposes something revolutionary. These cosmic phenomena might not be dead ends, but bridges to vast new universes or bounce points that trigger the genesis of an entirely new cosmos. This profound shift challenges the traditional view of spacetime as a continuous fabric and opens exhilarating possibilities for solving some of the most profound mysteries in cosmology. Through its unique lens, loop quantum gravity holds the potential to unravel the very nature of the universe itself, offering an unprecedented glimpse into the quantum origins of spacetime. The Planck scale plays an esteemed and pivotal role in theoretical physics, acting as the gatekeeper to the quantum realm where classical concepts of space and time begin to dissolve into a froth of uncertainty. Defined by Planck length, Planck time, Planck mass, and other fundamental units derived from universal constants, the Planck scale represents the unimaginably tiny arena where the effects of quantum gravity become significant. At this scale, roughly 10 to the minus 35 meters for Planck length and 10 to 44 seconds for Planck time, the smooth fabric of the universe, as predicted by general relativity, is theorized to break down into a quantized state. Here, gravity is expected to carry as much influence as the other three fundamental forces, electromagnetic, strong nuclear, and weak nuclear, which are well described by quantum field theory. The significance of the Planck scale extends beyond mere numbers. It embodies the frontier where the known laws of physics morph into uncharted territory, demanding a unified theory that reconciles quantum mechanics with general relativity. Theories such as string theory and loop quantum gravity strive to illuminate this esoteric domain, suggesting a universe woven from fine loops or vibrating strands of energy. Understanding phenomena at the Planck scale is not simply a quest to peer into the quantum crevices of spacetime, but a philosophical and scientific journey to decipher the cosmos's most fundamental nature. This unexplored territory of ultra-high energies, vastly beyond the reach of current particle accelerators, tantalizes physicists with the possibility of uncovering new physical laws fundamentally distinct from those known today. At energies near the Planck scale, where quantum gravitational effects become inescapable, the conventional framework of physics, built upon the pillars of quantum mechanics and general relativity, faces formidable challenges. It suggests that these realms might operate under principles yet to be conceived. This frontier, often associated with the universe's infancy moments after the Big Bang, could reveal exotic phenomena such as extra dimensions or the unification of all fundamental forces, commonly called the theory of everything. Such potential discoveries promise not only to expand our understanding of the universe's building blocks, but also to revolutionize technological advancements in ways we can barely imagine. The quest to probe these energies, though daunting, inspires cutting-edge experiments and theoretical frameworks, driving the innovation of more powerful particle accelerators and sophisticated cosmological observations. The hope is that ventures into this unknown will peel back the layers of the cosmic onion, exposing new laws of physics governing the high-energy regime and offering profound insights into the very essence of reality itself. Entanglement and quantum mechanics stand at the vanguard of a paradigm shift that challenges the bedrock of classical theories of the universe. Classical physics envisions objects with definable properties, influences constrained by the speed of light, and a reality governed by causality and determinism. However, quantum mechanics introduces entanglement, a phenomenon where particles become inseparably linked, such that the state of one, no matter the distance from its partner, instantaneously influences the state of the other. Einstein famously derided this as spooky action at a distance. This phenomenon defies classical physics, which posits that no information can travel faster than light. Furthermore, quantum mechanics reveals that at the subatomic level, particles exist in states of probability rather than definitive reality, only taking on concrete properties when observed or measured. This principle shatters the classical expectation of a deterministic universe, ushering in a reality where observation itself determines the state of physical systems. These quantum oddities do not merely question the nature of reality and space-time's fabric. They compel us to rethink the very foundation of existence. The implications ripple across physics and philosophy, challenging our most fundamental assumptions about causality, locality, and the nature of information itself. The journey into the depths of quantum gravity and the Planck scale is a voyage into the unknown, a convergence point where the smallest building blocks of matter meet the vastness of cosmic phenomena. It is a frontier teeming with mysteries, beckoning humanity to transcend its current understanding and reach for a unified theory that might finally illuminate the deepest workings of the cosmos. In this grand pursuit, every step forward, whether through bold theoretical proposals or cutting-edge experiments, brings us closer to grasping the true nature of space, time, and reality itself. It is a scientific odyssey that promises to redefine our place in the universe and the very fabric of existence that binds it all together. But the universe does not simply reveal its secrets. It challenges, puzzles, and pushes the boundaries of human understanding at every turn. It also fuels groundbreaking technologies like quantum computing and encryption, which harness the baffling phenomena of the quantum world, phenomena that defy the very foundations of classical physics. These quantum effects enable computations and encryptions inconceivable in classical mechanics, heralding a new era where information processing and security are revolutionized. Through its defiance of classical intuition, quantum mechanics beckons us to undertake a profound reassessment of our understanding of the cosmos itself. It promises not only a deeper comprehension of the universe's most enigmatic forces, but a radical transformation in how we perceive reality's underlying fabric. The frontier of theoretical physics is littered with profound mysteries that continue to challenge even the most brilliant minds. Among these puzzles, the nature of dark matter and dark energy stands out as one of the most perplexing enigmas. Dark matter constitutes approximately 85% of the universe's total matter, while dark energy accounts for roughly 70% of its total energy density. Despite their overwhelming presence, their fundamental properties and origins remain shrouded in mystery. This darkness casts long shadows over our understanding of cosmic structures and the accelerated expansion of the universe. It is as though a vast, invisible force shapes the cosmos, manipulating galaxies, stars, and the very fabric of space-time without revealing its true identity. Another deep and persistent mystery lies in reconciling the elegant framework of general relativity, which exquisitely describes the macroscopic world of gravity and spacetime, with quantum mechanics, the equally successful theory governing the subatomic realm. The quest to develop a theory of quantum gravity, one capable of seamlessly merging these two seemingly incompatible descriptions, remains one of the most formidable challenges in modern physics. The inability to unify gravity and quantum mechanics leaves fundamental questions about the true nature of spacetime and the cosmos unanswered, hinting at a reality far stranger and more complex than our current models suggest. Moreover, the universe's very existence rests on another profound puzzle. Why does matter dominate over antimatter? This imbalance, which allows galaxies, stars, planets, and ultimately life itself to exist, challenges our understanding of fundamental symmetries and the conditions prevailing moments after the Big Bang. The mechanisms behind this disparity are not fully understood, suggesting that new physics beyond our current theories awaits discovery. The imbalance hints at unknown processes that may rewrite our understanding of the cosmos at its most fundamental level. Adding to these cosmic riddles is the infamous information paradox surrounding black holes. Black holes, the remnants of collapsed stars with gravitational fields so intense that nothing can escape them, pose a conundrum that pits the principles of quantum mechanics against the inexorable grip of gravitational collapse. This paradox challenges the principle of information conservation in the universe and raises unsettling questions about the fate of information that falls beyond the event horizon. It presents a surreal boundary where known physics breaks down and our current understanding of reality frays at the edges. Together, these mysteries underscore the vastness of our ignorance and the potential for groundbreaking discoveries waiting just beyond our reach. They drive the quest for deeper, more comprehensive theories that not only aim to illuminate the shadows cast by our current knowledge, but to redefine the very fabric of reality as we perceive it. They promise a future in which the cosmos may be viewed through an entirely new lens, one where the nature of existence, time, and space itself could be understood in ways that today seem like science fiction. Amid these cosmic enigmas, one particularly striking phenomenon has captured the imagination of astronomers worldwide: fast radio bursts. These intense flashes of radio waves, each lasting mere milliseconds, emit as much energy as our sun does over several days. Since their discovery in 2007, fast radio bursts have perplexed scientists, sparking numerous theories and rigorous observational campaigns aimed at uncovering their origins. These mysterious signals predominantly appear to emanate from galaxies billions of light years away, far beyond our own Milky Way, adding further layers of intrigue to their elusive nature. One prevailing theory proposes that fast radio bursts result from cataclysmic astrophysical events, such as the collision of dense stellar remnants like neutron stars or the explosive deaths of highly magnetized neutron stars known as magnetars. Indeed, a groundbreaking breakthrough occurred in 2020 when astronomers traced a series of fast radio bursts to a known magnetar within our Milky Way. This discovery provided substantial evidence that at least some of these bewildering phenomena can be attributed to magnetar outbursts, immense bursts of energy released by these exotic stars with magnetic fields trillions of times stronger than Earth's. This revelation marked a significant milestone in our understanding of fast radio bursts, linking these mysterious signals to extreme astrophysical processes that push the limits of physics. Yet, despite this progress, many questions remain unanswered, reminding us that the cosmos is a vast, dynamic stage where phenomena both beautiful and baffling continue to unfold. Each discovery opens new doors, revealing the grandeur and complexity of the universe and fueling our relentless pursuit of knowledge. However, the story of fast radio bursts, or FRBs, does not end here. The astonishing diversity in their observed properties suggests that these enigmatic signals might not all share a single origin. Some FRBs erupt once in a brilliant flash, vanishing as quickly as they appear, leaving behind nothing but intrigue and mystery. Others, however, repeat, pulsing out radio waves multiple times from the same region of the sky. This fascinating variability hints at the possibility that multiple cosmic phenomena could be responsible for producing these bursts, painting a complex and layered picture of these perplexing celestial events. The cause and origins of FRBs remain a vibrant, ever-evolving field of research that challenges our understanding of the cosmos. Scientists are compelled to peer deeper into the vast reaches of space, searching for clues hidden in these fleeting flashes of radio light. Each burst carries secrets about the extreme physics governing the universe, offering tantalizing glimpses into energetic processes we have yet to fully comprehend. In parallel, cosmic rays present another cosmic puzzle: high-energy particles racing through space at nearly the speed of light. These particles slam into Earth's atmosphere, with energies far surpassing anything humanity has been able to recreate with our most powerful particle accelerators. How do these cosmic messengers achieve such staggering energies? This question has sparked intense investigation and debate among astrophysicists for decades. One of the leading theories suggests that the violent shock waves from supernova explosions act as natural accelerators. When the remnants of a supernova expand and collide with the interstellar medium, They create shock fronts, turbulent regions where particles may be repeatedly bounced back and forth, gaining energy with each pass through the shock, much like a cosmic pinball machine. These regions become cosmic crucibles where particles are propelled to astonishing velocities. Another potential source of these ultra-high energy cosmic rays lies in the supermassive black holes nestled at the centers of galaxies, including our own Milky Way. As matter spirals inward toward these gargantuan gravity wells, enormous jets of plasma are ejected at relativistic speeds into space. Particles trapped within these jets can be accelerated to mind-boggling energies, contributing to the cosmic ray population. Magnetars, exotic neutron stars with incredibly powerful magnetic fields, also enter the stage as prime candidates for cosmic ray acceleration. Their magnetic fields decay rapidly, releasing tremendous amounts of energy capable of boosting particles to the observed energies of cosmic rays. Despite these promising theories, the precise mechanisms and astrophysical sites responsible for the highest energy cosmic rays still elude definitive explanation. The mystery deepens because cosmic rays do not travel in straight lines. Their paths are deflected by magnetic fields threading through space, making it nearly impossible to trace them back to their sources. This enigma continues to fuel research and debate, pushing the boundaries of our knowledge about the universe's most extreme particle accelerators. In the realm of cosmic mysteries, the WOW signal stands out as one of the most tantalizing and unexplained anomalies. Detected in 1977 by the Big Ear radio telescope, this powerful radio burst has defied conclusive explanation for decades. Its characteristics, strong, narrow band, and seemingly artificial, captured the imagination of scientists and the public alike. The WOW signal sparked speculation about extraterrestrial intelligence because it did not match any known natural cosmic sources or terrestrial interference. Beyond the tantalizing possibility of contact with alien civilizations, the WOW signal and other unexplained anomalies hold profound implications. They reveal the vastness of our ignorance about the cosmos, exposing significant gaps in our current models and theories. The pursuit of explanations for these mysterious phenomena drives innovation in observational techniques and technologies, often propelling scientific methodologies forward and leading to serendipitous discoveries unrelated to the original phenomena under study. Moreover, these mysteries serve as crucial reminders of the need for skepticism and rigor in scientific inquiry. The allure of jumping to sensational conclusions can cloud judgment, underscoring the importance of adhering to principles of verifiability, repeatability, and critical evaluation. Anomalies challenge the scientific community to remain open to novel hypotheses and theories while maintaining a discerning eye toward evidence and interpretation. Ultimately, exploring unexplained phenomena like the WOW signal enriches the scientific endeavor, fueling a sense of wonder and curiosity that drives humanity's quest for knowledge. Whether these anomalies eventually yield mundane explanations or lead us to revolutionary breakthroughs, they play an indispensable role in the iterative process of understanding the universe and our place within it. Turning to cosmic magnetic fields, their study opens a fascinating window into the myriad forces that shape the cosmos. These magnetic fields permeate space on all scales, from the smallest planetary systems to the largest galactic clusters. They are not only ubiquitous, but also fundamental in shaping the behavior and evolution of astronomical objects and structures. Magnetic fields influence star formation by regulating the collapse of gas clouds, govern the dynamics of cosmic jets, and shape the interstellar medium's turbulent flows. In galaxies, magnetic fields help channel cosmic rays and affect the distribution of matter. On the grandest scales, they weave through the cosmic web, influencing how matter clumps together to form the large-scale structure of the universe. Measuring and understanding these magnetic fields requires innovative techniques, including polarized light observations, Faraday rotation measurements, and increasingly sensitive radio telescopes. As our tools improve, we uncover more about the tangled, invisible magnetic forces that play a silent yet powerful role in cosmic evolution. The combined study of FRBs, cosmic rays, anomalous signals like the WOW signal, and cosmic magnetic fields paints a portrait of a universe that is far more dynamic and mysterious than once imagined. Each discovery invites new questions, each mystery fuels new research, and every breakthrough pushes the boundaries of human understanding further into the cosmic abyss. We stand at the frontier of discovery, with the universe revealing its secrets in bursts of radio light, streams of high-energy particles, fleeting signals, and invisible magnetic threads. These phenomena remind us that our grasp of the cosmos is still incomplete, urging us onward in an endless journey to comprehend the vast, wondrous expanse that surrounds us. But also instrumental in dictating the dynamics of cosmic plasma, magnetic fields weave an invisible tapestry across the vast expanse of the universe, guiding the birth of stars, shaping the grand architecture of galaxies, and controlling the restless journey of high-energy cosmic rays. These magnetic forces, subtle yet powerful, serve as the silent architects behind the celestial phenomena we observe, influencing the universe at every scale. One of the most profound revelations gleaned from the study of cosmic magnetic fields lies in their crucial role in galaxy formation and evolution. These magnetic fields, deeply intertwined with the interstellar medium, the vast clouds of gas and dust that float between stars, act as regulators in the delicate ballet of star formation. By influencing the collapse of molecular clouds, magnetic fields help govern when and where stars ignite, steering the cosmic cycle of birth and death that fuels the universe. Understanding these magnetic fields is like uncovering the hidden rules of a complex cosmic game, revealing how forces collide, cooperate, and compete to forge the stars that light up the night sky. Beyond star formation, cosmic magnetic fields are essential to our grasp of cosmic ray propagation. These charged particles, speeding through the galaxy at nearly the speed of light, are scattered and redirected by magnetic fields, which act as cosmic traffic controllers, shaping their paths and the distribution of radiation that permeates space. The intricate dance between cosmic rays and magnetic fields offers astronomers invaluable insights into the origins of these rays and the magnetic environments through which they travel, illuminating the processes that unfold in some of the universe's most extreme conditions. On scales that dwarf entire galaxies, magnetic fields extend into the vast voids of intergalactic space, whispering secrets from the earliest epochs of the universe. These intergalactic magnetic fields, though faint and elusive, may carry the imprints of cosmic inflation, the rapid expansion thought to have occurred moments after the Big Bang. They stand as ancient relics, offering astronomers tangible links to the universe's infancy and the cosmic evolution that followed. Through both observation and theory, the study of cosmic magnetic fields has become a cornerstone of modern cosmology and astrophysics. As our instruments grow more sensitive and our models more sophisticated, the mysteries of cosmic magnetism promise to unlock profound insights into the very fabric of the cosmos, its structure, dynamics, and history. And yet the questions only deepen as we turn our gaze closer to home, to our own star, the Sun. The possibility that the Sun might emit unknown particles pushes the boundaries of astrophysics and particle physics into new, thrilling territories. The Sun, a maelstrom of nuclear fusion and electromagnetic fury, continuously floods space with a torrent of known particles, neutrinos born from nuclear reactions deep within, electromagnetic radiation spanning the spectrum, and the solar wind, a relentless stream of charged particles like electrons, protons, and alpha particles. But could there be more? Particles so elusive or exotic that we have yet to detect them? Solar neutrinos, for instance, are already a gateway to new physics. Produced in staggering numbers by the Sun's nuclear engine, these nearly massless particles slip through matter effortlessly, passing through the Earth and ourselves by the billions every second without leaving a mark. Their detection has revolutionized particle physics, revealing the phenomenon of neutrino oscillation, a discovery that upended previous assumptions by showing neutrinos have mass. This finding opened pathways beyond the standard model, the prevailing framework of particle physics. Beyond neutrinos, theorists speculate about other exotic particles, axions and sterile neutrinos that could emerge from the Sun's core under certain conditions. Axions, hypothetical particles proposed to resolve the strong CP problem in quantum chromodynamics, also appear as promising candidates for dark matter. If axions do exist and are produced by solar processes, detecting them would not only illuminate the inner workings of the Sun, but could also solve some of the universe's deepest mysteries, from the nature of dark matter to fundamental particle physics. Current and upcoming experiments designed to catch these elusive particles or to probe neutrino properties more deeply hold the promise of unveiling new layers of reality. Such discoveries could rewrite textbooks, reshaping our understanding of particle physics, astrophysics, and cosmology alike. While still speculative, the search for unknown solar particles epitomizes the profound shifts that seemingly simple questions can provoke in our comprehension of the universe. Among these questions lies the enigma of antimatter, matter's mysterious counterpart bearing the opposite electric charge. The study of antimatter pushes the frontiers of physics, challenging our fundamental understanding of the cosmos and the forces that govern it. Antimatter exists as one of the most tantalizing puzzles in modern science. Why does our universe appear dominated by matter when the laws of physics suggest that matter and antimatter should have been created in equal amounts during the Big Bang? This imbalance, called baryon asymmetry, remains unresolved, driving scientists to explore beyond known physics. Investigations into antimatter production, annihilation, and behavior are not only vital for unraveling cosmic history, but also hold practical implications for advanced technologies and space exploration. Cosmic magnetic fields, solar particle emissions, neutrinos, axions, antimatter, each represents a thread in the grand tapestry of cosmic inquiry. Together, they form a complex mosaic revealing the universe's deepest secrets, stretching from the smallest particles born within the sun's core to the largest magnetic structures, threading galaxies and the vast expanses beyond. As humanity's curiosity propels our instruments to new heights and sharpens our theoretical tools, we stand on the cusp of breakthroughs that will redefine our place in the cosmos, revealing a universe richer and more mysterious than ever imagined. But also holds potential keys to unraveling some of the universe's deepest mysteries. Antimatter remains one of the most enigmatic and captivating puzzles in modern physics. Among the perplexing questions that surround antimatter, none is more fundamental than the matter-antimatter asymmetry observed across the cosmos. According to the prevailing theories that stem from the Big Bang model, matter and antimatter should have emerged in precisely equal amounts during the universe's earliest moments. Yet when astronomers peer into the vast expanse of space, what they observe is a universe overwhelmingly dominated by matter, with antimatter conspicuously scarce and elusive. This stark imbalance ignites a profound question. What happened to all the antimatter? Why did matter prevail so dominantly, and was there some mechanism in the primordial universe that favored the production or survival of matter over antimatter? These questions do not merely touch on cosmological curiosity, but pierce to the very core of our understanding of the universe's birth and evolution. Solving this asymmetry would provide critical insights into the fundamental conditions and laws that governed the cosmos shortly after its inception, reshaping our comprehension of reality itself. Furthermore, antimatter serves as a unique and powerful probe into the fundamental symmetries of physics. Experiments involving antiparticles allow physicists to test the principles of charge parity time, CPT symmetry, a cornerstone concept proposing that the laws of physics should remain invariant if charge, parity, and time are simultaneously reversed. Any observed violation of CPT symmetry during antimatter experiments could herald new physics beyond the current standard model, challenging our deepest assumptions about the fundamental forces and particles that construct the universe. The quest to detect such violations is more than academic. It is a frontier where the fabric of known physics may unravel or be woven anew. Additionally, the behavior of antimatter in gravitational fields remains one of the least explored and most tantalizing frontiers in physics. Theoretical models predict that antimatter should respond to gravity identically to matter, falling in the same manner within a gravitational field. However, direct experimental verification is notoriously difficult. The challenge lies in antimatter's inherent tendency to annihilate immediately upon contact with ordinary matter, making precise measurements in gravitational contexts exceedingly complex. Confirming or refuting this aspect of antimatter's interaction with gravity could have far-reaching implications for gravitational theory, dark matter research, and models describing the universe's overall structure and fate. The large-scale structure of the universe itself reveals another mesmerizing cosmic enigma: the irregular distribution of galaxies. Vast voids and filamentous structures stretch across the universe in a breathtaking cosmic web, captivating astronomers and cosmologists alike. This intricate architecture, characterized by dense clusters of galaxies separated by enormous empty regions, reflects the universe's complex formation history and underlying physics. To explain this uneven cosmic tapestry, scientists turn to theories involving dark matter and the inflationary model of the early universe. Dark matter, an invisible and mysterious substance that neither emits nor absorbs electromagnetic radiation, comprises approximately 85% of all matter in the universe. While it cannot be observed directly, its presence is inferred through gravitational effects on visible matter, the motion of galaxies, and the subtle imprints left on the cosmic microwave background radiation. The prevailing theory holds that shortly after the Big Bang, the universe underwent tiny quantum fluctuations, minute variations in density that were exponentially magnified during a period of rapid expansion called cosmic inflation. These amplified fluctuations became the primordial seeds for the uneven distribution of dark matter. Over billions of years, dark matter clumped together under the force of gravity, creating an elaborate scaffold on which ordinary matter could gather and coalesce. This process of structure formation is believed to be the foundation of the cosmic web, explaining why galaxies formed preferentially in regions of higher dark matter concentration. These dense zones evolved into the filamentous structures and galaxy clusters observed today. Meanwhile, regions with sparse dark matter developed into vast cosmic voids, expansive, nearly empty spaces where few galaxies reside. The gravitational dance between dark matter and ordinary matter is thus a central driver in sculpting the large-scale structure of the universe. Complementing this picture is the cosmic microwave background radiation, a relic glow from the early universe that offers a snapshot of its infancy. Minute temperature variations in this ancient radiation provide clues to the initial density fluctuations that, under gravity's influence, eventually led to the rich, uneven distribution of galaxies spanning the cosmos. Through a combination of astronomical observations, detailed simulations, and sophisticated experiments, scientists continue to refine their understanding of dark matter's elusive nature and the dynamics of cosmic inflation. These endeavors push the boundaries of human knowledge, seeking to piece together the profound narrative of how the universe emerged from a near-uniform state into the awe-inspiring complexity we witness today. Each discovery inches us closer to unraveling the tapestry of cosmic origins, revealing how antimatter, dark matter, and the primordial forces intricately interwove to shape the grand cosmic story. And these efforts do not merely illuminate the processes that have sculpted the vast expanses of the cosmos. They unveil a profound interplay between the visible and invisible components of the universe, weaving together a far more comprehensive and intricate picture of its grand design. The Great Attractor and the Great Wall stand as two of the most remarkable phenomena, emblematic of the awe-inspiring scale and staggering complexity of the cosmos. These colossal structures dominate the cosmic landscape, reshaping our understanding of the universe's architecture and the forces that govern it. The Great Attractor, an enigmatic gravitational anomaly, lies approximately 220 million light-years away, nestled in the direction of the constellations Hydra and Centaurus. This mysterious region exerts a powerful gravitational pull, influencing not only our home galaxy, the Milky Way, but hundreds of others scattered within a radius spanning millions of light-years. Though it remains partially obscured by the dense plane of the Milky Way, which complicates direct observation, the Great Attractor is believed to be a gargantuan concentration of galaxies, hot gas, and elusive dark matter. Its significance extends far beyond mere curiosity. It stands as critical evidence for the existence of superstructures in the universe that dominate the cosmic dance of galactic motion, molding the large-scale structure of the cosmos itself. Equally monumental is the Great Wall, more formally known as the Sloan Great Wall. This cosmic behemoth stretches over 1 billion light-years and represents one of the largest known superstructures in the observable universe. Positioned roughly 1 billion light-years from Earth, The Great Wall is a vast filament of galaxies bound together in an intricate network that defies the once prevalent notion of a homogeneous universe at large scales. Instead, it reveals the cosmos as a breathtaking tapestry of galaxy clusters, filaments, and enormous voids, a cosmic web of staggering complexity. The discovery of the Great Wall profoundly challenged existing paradigms and sparked a renewed quest to understand the fundamental forces and processes that have shaped the universe over billions of years. Together, the Great Attractor and the Great Wall illuminate the pivotal role of gravity in organizing matter on a grand scale. Gravity's influence orchestrates the distribution and movement of galaxies across incomprehensible distances, sculpting the cosmic web itself. Yet, these phenomena also beckon scientists to probe deeper into the enigmatic nature of dark matter and dark energy, mysterious constituents that are thought to underpin the formation and evolution of such immense superstructures. By unraveling the secrets embedded in these colossal formations, astronomers and cosmologists aim to decode the narrative of cosmic evolution, shedding light on the fundamental principles that govern the universe's structure and dynamics. Intriguingly, anomalies in cosmic radiation patterns add another layer of mystery to this quest. These anomalies hold tantalizing potential to hint at new physics beyond the current boundaries of human knowledge. Cosmic radiation, encompassing the cosmic microwave background, CMB, radiation, and high-energy cosmic rays, forms the observational cornerstone for cosmology and particle physics alike. Yet, when unexpected patterns or irregularities emerge within this cosmic backdrop, they challenge long-held paradigms and ignite the pursuit of novel theoretical frameworks. Take, for example, the CMB, often described as the afterglow of the Big Bang. Within this ancient radiation, scientists have detected peculiar anomalies such as the cold spot, unexplained asymmetries, and unusual alignments in temperature fluctuations. These irregularities have fueled intense debate and speculation, inspiring theories ranging from the existence of vast cosmic voids to the tantalizing hypothesis of other universes residing within a multiverse framework. Each anomaly acts as a potential portal, inviting us to peer beyond the veil of conventional cosmology. Similarly, the behavior and origin of high-energy cosmic rays, particles accelerated to energies far beyond what human-made accelerators can achieve, remain shrouded in mystery. These particles bombard the Earth incessantly, yet their precise sources and mechanisms of acceleration are still elusive. Anomalous patterns in their distribution, origin, or interactions with cosmic backgrounds could illuminate the nature of dark matter, hint at previously undiscovered fundamental particles, or even reveal novel astrophysical phenomena yet to be comprehended. The search for explanations of these cosmic anomalies is more than an academic exercise. It drives the development of innovative theoretical models and inspires the proposal of new cosmic constituents. Each anomaly is a clue, a whisper from the universe urging humanity to venture further into the unknown. It compels scientists to rethink the foundations of physics and cosmology, pushing the boundaries of human understanding and expanding the frontier of what is conceivable. In this cosmic odyssey, the Great Attractor and the Great Wall are but two monumental milestones. Yet they represent the broader story of the universe's vast, dynamic, and often mysterious nature. As technology advances and observational tools grow ever more sophisticated, humanity stands on the precipice of uncovering deeper truths that may redefine our place in the cosmos and reveal the intricate choreography that governs the grand design of all existence. And this vast cosmic landscape holds secrets that go far beyond the familiar confines of our known physics. It can include extensions to the standard model of particle physics, where hidden particles and forces might be lurking just beyond our current reach. It can embrace novel mechanisms of particle acceleration, revealing the cosmic engines that propel matter to energies unfathomable on Earth. It can even challenge the very fabric of space-time itself, suggesting it may be more complex and dynamic than Einstein ever imagined. Moreover, these anomalies and mysteries do not simply baffle. They drive the relentless advancement of observational technologies. Scientists, armed with curiosity and ingenuity, strive to gather ever more precise data. Their goal, to confirm or refute the tantalizing presence of new physics hidden in the shadowy expanse of the cosmos. To this end, space telescopes have become our far-reaching eyes, probing corners of the universe that were once inaccessible, unveiling the unknown known with unparalleled clarity. Among their most astonishing discoveries are signals so enigmatic that they have sent ripples of excitement through the scientific community, sparking a whirlwind of speculation and intense research. Known as fast radio bursts, or FRBs, these phenomena are intense, fleeting flashes of radio waves lasting mere milliseconds. Yet in that instant, they unleash as much energy as our sun emits over the course of days. First detected in 2007, the origins of these bursts remain one of the most tantalizing puzzles in modern astronomy. Theories abound. Some propose starquakes, sudden seismic events on neutron stars, as the source. Others suggest highly magnetized neutron stars known as magnetars. Still more controversial is the idea that these signals could be artificial in origin, hinting at alien spacecraft sending messages across the void. Despite all hypotheses, no definitive explanation has yet emerged. These fleeting, powerful signals stand as a humble reminder of how much remains unknown, inviting both scientists and the public into a grand cosmic detective story that challenges our deepest assumptions about the universe. And the cosmos itself is an expanse beyond comprehension, vast beyond measure. It contains hundreds of billions of galaxies, each teeming with countless stars and even more planets. In this immense ocean of stars, the likelihood that life exists elsewhere moves beyond the realm of science fiction and edges ever closer to scientific plausibility. The discovery of extraterrestrial life, even in its simplest microbial form, would mark a paradigm shift in human thought and society unparalleled by any previous scientific breakthrough. At its core, such a discovery would challenge our fundamental understanding of life itself. It could potentially rewrite biology textbooks, offering profound new insights into the origins and evolution of life on Earth. The realization that we are not alone in the universe could spark profound philosophical and theological introspection, shaking long-held beliefs about humanity's place in the cosmos. Moreover, the discovery of extraterrestrial life could foster a renewed sense of unity among Earth's inhabitants, highlighting our shared identity as custodians of a small, fragile planet in the vast cosmic wilderness. On a more practical level, it would accelerate space exploration efforts, driving technological advancements and possibly fostering unprecedented international collaboration to study and perhaps even communicate with other life forms beyond our world. Despite the profound disruptions such a monumental discovery might cause, it would open new horizons for understanding, cooperation, and exploration, marking a new chapter in human history. In the search for life beyond Earth, biosignatures, subtle fingerprints of biological activity, hold the key to unlocking some of the deepest mysteries of existence. These biosignatures may take many forms. Specific molecules such as oxygen and methane that often indicate biological processes, or more complex organic compounds hinting at the presence of life. By analyzing the atmospheric composition of distant exoplanets using spectroscopy, a technique that unfolds the spectrum of light to identify chemical fingerprints, scientists seek these telltale signs across the vast reaches of space. When a planet passes in front of its star, the starlight filters through the planet's atmosphere. If biosignatures are present, they absorb specific wavelengths of this light, creating distinctive patterns detectable by our most advanced space telescopes. This method, though fraught with challenges due to the faintness of signals and enormous distances involved, offers a promising window into identifying worlds that might harbor life. The launch of more advanced space telescopes equipped with cutting-edge spectroscopic capabilities brings humanity closer than ever before to answering the timeless question, are we alone in the universe? Through the meticulous study of biosignatures, scientists around the world hold a cautious but hopeful outlook on uncovering the cosmic story of life. The conditions required for a planet to support life, at least as we understand it, depend on a delicate balance of factors, often described as the Goldilocks zone, where a planet is neither too hot nor too cold. This habitable zone ensures the presence of liquid water, the essential ingredient for life on Earth. Yet even within this zone, many other factors such as atmospheric composition, magnetic fields, and geological activity play crucial roles in creating a stable environment capable of sustaining life. This pursuit of knowledge is not just a scientific quest, but a journey into the heart of our own existence. It compels us to reflect on what life means, how it arises, and where else it might thrive in the vast cosmos. As we push the boundaries of exploration, new questions arise, drawing humanity ever deeper into the cosmic mystery. Our journey to understand the universe's secrets unfolds in an era of unprecedented discovery, with each revelation acting as both a beacon and a challenge. From the microscopic fingerprints of life on distant worlds to the enigmatic bursts of energy flashing across the cosmos, we are participants in an extraordinary chapter of human history, one that promises to reshape our understanding of the universe and our place within it. But just the right conditions for liquid water to exist define a special zone around stars, known as the habitable zone. This region varies depending on the star's size and heat output, yet it is precisely within these bounds that liquid water, a universal solvent and life's essential medium, can persist. Liquid water is not merely a luxury. It is fundamental because it enables the biochemical reactions that underpin all known life. However, the presence of water alone does not guarantee a life-supporting planet. A stable atmosphere is equally vital, serving as both shield and thermostat. It protects organisms from the relentless barrage of harmful space radiation and tempers the planet's climate, maintaining a balance that allows life to flourish. The atmosphere's composition matters deeply. Elements like carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus are considered essential building blocks of life as we understand it. Yet, beyond these elemental prerequisites, geological activity plays a crucial role in sustaining habitability. Volcanic eruptions, for example, recycle minerals and gases back into the environment, replenishing resources and stabilizing the atmosphere over geological timescales. This dynamic interaction between atmosphere, surface, and interior is a delicate dance that Earth has mastered, nurturing life for billions of years. While these criteria outline what life on Earth depends upon, the search for extraterrestrial life forces us to challenge our assumptions. The universe is vast and varied, and life elsewhere might not adhere to the same Earth-centric template. In fact, the hunt for alien life often carries an unconscious bias, presuming that life must be carbon-based and reliant on water. But what if life could arise in forms utterly alien to us? Scientists speculate about alternative biochemistries, imagining life based on silicon, a chemical cousin of carbon, or even life that exploits solvents other than water. Silicon, sharing many chemical properties with carbon, opens intriguing possibilities. Silicon-based life forms could thrive in environments utterly hostile to carbon-based organisms, perhaps on planets with harsh conditions that would annihilate life as we know it. Similarly, while water sustains terrestrial life, other liquids, such as liquid methane or ammonia, might serve as life solvent under the right temperature and pressure conditions. Worlds like Titan, Saturn's largest moon, with its frigid lakes of methane and ethane, inspire speculation about life forms evolving mechanisms radically different from those on Earth to harness energy, grow, and reproduce. These ideas remain speculative, yet expand the scope of astrobiology, inviting a more inclusive search for life beyond our planet. They remind us that life, if it exists elsewhere, might be stranger and more diverse than our earthbound imaginations have dared to conceive. Defining life from a cosmic perspective plunges scientists into a profound web of philosophical, biological, and astrobiological challenges. On Earth, life is broadly characterized by metabolism, growth, responsiveness to stimuli, and reproduction. These criteria, however, are deeply rooted in carbon-based, water-reliant organisms. The vastness of the cosmos suggests that extraterrestrial life might not follow the same rules. Could a silicon-based entity existing in a liquid methane environment on a distant moon exhibit forms of organization and energy use unlike anything terrestrial life has ever demonstrated? Would we recognize it as alive? The challenge extends to detection itself. Our instruments and search strategies are calibrated to detect biosignatures mirroring Earth's life: oxygen, methane, organic molecules, patterns of electromagnetic radiation. But such criteria might overlook entirely different manifestations of life. Moreover, the boundary between complex, self-organizing, non-living systems and true living organisms becomes blurred in unknown cosmic realms, complicating our ability to define and detect life unambiguously. To confront these challenges requires an interdisciplinary approach, weaving insights from biology, chemistry, astronomy, and philosophy to conceive a universal definition of life. This pursuit not only expands our understanding of potential life forms and habitats, but deepens our appreciation for the fundamental processes animating the natural world. Engaging with these questions urges humanity to move beyond terrestrial biases to contemplate the myriad ways the cosmos might harbor the marvelous phenomenon we call life. Extremophiles, organisms thriving in environments once thought utterly inhospitable, are pivotal in broadening our concept of life's resilience and potential habitats. These hardy creatures inhabit some of Earth's most extreme environments: the scorching hydrothermal vents on the ocean floor, acidic hot springs, crushing deep-sea trenches, and the frozen deserts of Antarctica. Their existence testifies to life's extraordinary adaptability and hints that life might survive under conditions far removed from those typical on Earth. By studying extremophiles, scientists uncover biochemical and genetic adaptations that enable survival in extreme conditions, adaptations that expand the criteria for habitability and challenge long-held notions about where life can exist. This knowledge suggests that many planets and moons previously dismissed as uninhabitable may in fact be capable of supporting life, albeit life unlike what we have previously conceived. For instance, microbes on Earth that utilize sulfur compounds for energy instead of sunlight support the possibility of life thriving in subsurface oceans of icy moons like Europa, where sunlight does not penetrate. Extremophiles also refine our search for biosignatures by demonstrating that life can not only endure but actively metabolize in chemically harsh environments. This broadening of perspective compels us to rethink the search for life beyond Earth. It encourages the development of novel detection methods sensitive to diverse chemical and physical signatures. It propels missions to worlds once considered barren, transforming them into prime candidates for exploration and study. In this way, the study of extremophiles serves as both inspiration and guide, opening windows into the profound and astonishing potential for life elsewhere in the cosmos. The journey to understand life's cosmic diversity continues to unfold. As we probe the mysteries of distant planets and moons, refine our instruments and theories, and grapple with the philosophical implications of life's definition, we come closer to answering one of humanity's most enduring questions: are we alone in the universe? The answer, wherever it may lie, promises to reshape our understanding of biology, chemistry, and the very nature of existence itself, but also flourish in environments with chemistries vastly different from Earth's surface. Extremophiles redefine the very boundaries of life as we understand it. As humanity extends its reach deeper into the solar system, sending probes to Mars, Titan, and beyond, equipped with sophisticated instruments designed to detect even the faintest signatures of life, the study of these hardy organisms ensures that our search remains attuned to the broadest spectrum of possibilities. These life forms, diverse and tenacious, thrive where the conditions challenge the survival of most known organisms, offering a blueprint for what alien life might look like. Venus, with its infernal environment, stands as a testament to nature's extremes. Its thick, toxic atmosphere, composed predominantly of carbon dioxide, cloaks the planet in a suffocating shroud. Surface temperatures soar to levels hot enough to melt lead, and the atmospheric pressure crushes with a force nearly 100 times that of Earth's sea level. At first glance, Venus seems an unlikely candidate to host life. However, recent scientific inquiries have shifted attention to its upper atmosphere, specifically the acidic cloud decks where temperatures and pressures become more Earth-like. It is here, suspended in a layer of sulfuric acid droplets and cloaked in perpetual twilight, that microbial life might find refuge. The discovery of phosphine gas in Venus's atmosphere sparked widespread intrigue. On Earth, phosphine is a molecule strongly linked to biological processes, its presence suggesting that similar processes could be occurring in the planet's clouds, hinting at the tantalizing possibility of aerial microbial life. This discovery challenged our preconceptions about where life can exist and opened new avenues of research into life's adaptability. Moving outward, the gas giants Jupiter, Saturn, Uranus, and Neptune present a different suite of challenges altogether. Without solid surfaces and dominated by crushing pressures and extreme temperatures, these colossal planets themselves are unlikely to harbor life as we know it. Yet, their many moons have become the new frontiers in the quest for extraterrestrial life. Jupiter's moon Europa and Saturn's moon Enceladus, for instance, are wrapped in thick, icy crusts beneath which lie vast subsurface oceans. These hidden seas, shielded from cosmic radiation and extreme surface conditions, resemble deep oceanic environments on Earth where extremophiles thrive. Life in these alien oceans might depend not on sunlight, but on chemosynthesis, extracting energy from chemical reactions occurring within the rocky ocean floors, much like bacteria near Earth's hydrothermal vents. Such life would be fundamentally different from terrestrial organisms, offering new paradigms for biology. Though direct evidence remains elusive, the possibility that these moons harbor life reshapes our understanding of where life might flourish in the universe. The discovery of microbial life on Mars would be a watershed moment in human history, a monumental milestone in our quest to understand the cosmos and our place within it. It would irrevocably affirm that life is not unique to Earth, dispelling centuries of speculation about our planet's singularity as a cradle for biology. The scientific implications would be profound and far-reaching. It would ignite a new era of astrobiology, driven by the urgent need to unravel how life emerged independently on Mars and Earth. Researchers would scrutinize Martian microbes, comparing their genetic, biochemical, and physiological characteristics to those of Earth's life forms. This comparative analysis could reveal universal principles of biochemistry, as well as planet-specific adaptations, offering deep insights into the resilience and adaptability of life itself. Beyond pure science, the discovery would carry significant practical consequences for future Mars exploration and colonization. The presence of life would necessitate stringent planetary protection protocols to prevent harmful cross-contamination, safeguarding both Earth's and Mars's biospheres. More broadly, it would elevate the ethical considerations and complexities surrounding human activity on Mars, ensuring that exploration does not disrupt native ecosystems. This discovery would answer one of humanity's oldest and most profound questions. Are we alone in the universe? Yet it would also raise new questions about the nature of life, its origins, and its distribution across the cosmos, propelling humanity into a bold new frontier of exploration and discovery. The Fermi paradox, named after the physicist Enrico Fermi, encapsulates the profound contradiction between the high probability of extraterrestrial civilizations existing somewhere in the vast universe and our complete lack of evidence or contact with them. This paradox ignites vigorous debate across scientific, philosophical, and speculative realms, each interpretation shedding light on our cosmic predicament. One such interpretation is the rare Earth hypothesis, which argues that while simple life might be common, the complex and precise sequence of events that led to intelligent, technologically advanced life on Earth is extraordinarily rare. According to this view, the myriad conditions, planetary, biological, geological, and even astronomical, required for such evolution are so improbable that we might be alone in our galaxy or even the observable universe as the only current sapient observers. Alternatively, the silence may be a product of our technological and temporal limitations. The immense distances separating potential civilizations, combined with the finite speed of light, mean that signals from other intelligent beings might not yet have reached us, or that we are simply not listening at the right frequency or moment. Advanced civilizations might employ communication methods beyond our current understanding, or choose deliberate isolation from less advanced societies like ours, perhaps due to existential concerns or cultural choices. A more ominous interpretation involves the Great Filter hypothesis, suggesting that life in the universe faces one or more insurmountable obstacles, preventing it from advancing to the stage of interstellar colonization or detectable communication. This filter might lie in the distant past, such as the initial emergence of life, or the leap from simple prokaryotic to complex eukaryotic cells, or it may lie ahead, posing a dire challenge for humanity's future. The nature and timing of this filter remain deeply speculative, but carry profound implications for our species and our future. Each of these perspectives on the Fermi paradox underscores the limits of our current search for extraterrestrial life. and challenges us to expand our scientific, philosophical, and technological horizons. They compel us to confront not only the possibility of life elsewhere, but the fundamental nature of life itself, its origins, evolution, and fate. In exploring these mysteries, we deepen our understanding of ourselves and the cosmos, driven by the enduring human desire to find our place in the vastness of space, but also provokes deeper questions about our understanding of life, evolution, and our place in the cosmos. The profound silence that has greeted our search for extraterrestrial intelligence serves as a humbling reminder of the mysteries that continue to elude us. It highlights the speculative nature of our quest to find others like ourselves in the vastness of the universe. Yet it is within this silence that the greatest challenge lies, to understand not only what we seek, but also how we seek it, and what it means if we find nothing or everything. The coming era promises to be transformative. The next generation of telescopes, both ground-based and spaceborne, are poised to revolutionize our understanding of the cosmos, pushing the boundaries of exploration further than humanity has ever dared. These marvels of engineering and science represent the culmination of centuries of astronomical curiosity, technological innovation, and scientific ambition. Among the most groundbreaking are the James Webb Space Telescope, the Extremely Large Telescope, the 30-meter telescope, and the Giant Magellan Telescope. Together, they will open new windows onto the cosmos, providing unprecedented clarity and depth. Launched in December 2021, the James Webb Space Telescope embodies a leap forward in humanity's ability to peer into the cosmic past. Designed to observe the universe primarily in the infrared spectrum, it can penetrate dense clouds of cosmic dust, unveiling the earliest epochs of star, galaxy, and planetary system formation. It allows astronomers to gaze further back in time than any telescope before it, into an era when the universe was in its infancy and the first cosmic structures were just beginning to take shape. By revealing the birthplaces of stars and the scaffolding of galaxies, the James Webb Telescope sheds light on fundamental questions about our cosmic origins and the processes that have shaped everything we see today. Meanwhile, on Earth's surface, colossal observatories are rising in some of the most remote and pristine environments on the planet. The Extremely Large Telescope, currently under construction in the Atacama Desert of Chile, will boast a primary mirror 39 meters in diameter, the largest optical and near-infrared telescope ever built. Its immense size will grant astronomers unparalleled clarity and sensitivity, enabling direct imaging of exoplanets orbiting distant stars. This telescope will delve into the accelerating expansion of the universe, offer new insights into the enigmatic dark matter and dark energy that govern cosmic dynamics, and sharpen our understanding of the grand cosmic web. It will bring distant galaxies into sharper focus, allowing us to study their life cycles and evolutionary histories with extraordinary detail. The 30-meter telescope, planned for construction atop Mauna Kea in Hawaii, and the Giant Magellan Telescope, also located in Chile, will complement these efforts by pushing the limits of observational astronomy even further. The TMT will investigate the formation of early galaxies and black holes, peering deep into the cosmos to capture light that has traveled billions of years. Meanwhile, the GMT will excel in discovering and characterizing exoplanets, focusing on analyzing their atmospheres for potential biomarkers, signatures of life. These telescopes will collectively offer a deeper, more detailed view of the universe, potentially revealing new physical phenomena and unlocking secrets of dark matter, dark energy, and the intricate formation of cosmic structures. Perhaps most tantalizingly, they will illuminate the conditions necessary for life beyond Earth. By observing the atmospheres of distant worlds and analyzing the chemical signatures within them, these instruments hold the promise of answering one of humanity's most profound questions. Are we alone? Their observations could redefine our cosmic narratives and place humanity within a broader, more complex cosmic context, shifting our perception of our place in the universe. Alongside these physical instruments, artificial intelligence and machine learning are emerging as revolutionary tools that will redefine how we interpret the universe. The enormous volumes of data generated by modern astronomical observatories have long exceeded the capacity for manual analysis. AI and machine learning offer powerful solutions to this data deluge, capable of sifting through terabytes of information, identifying patterns, and detecting anomalies that might otherwise go unnoticed by human researchers. These technologies can automate the classification of galaxies, spot transient cosmic phenomena such as supernova or fast radio bursts, and do so with unprecedented speed and accuracy. Machine learning algorithms trained on vast datasets are continually refined to recognize specific cosmic objects or events, drastically reducing the time required for discovery and enabling near real-time data analysis. This not only accelerates scientific progress, but also opens the door to discoveries that might otherwise be missed due to the sheer volume and complexity of data. Moreover, AI extends beyond data processing. It enables the simulation of complex cosmic processes. Through advanced computational models, scientists can explore the dynamics of galaxy formation, star development, and planetary system evolution. These simulations allow researchers to test hypotheses and explore scenarios impossible to observe directly, thereby pushing the boundaries of theoretical astrophysics. AI-driven simulations help unravel the interplay of forces shaping the cosmos and offer predictions that can be tested with observational data. Perhaps most exciting is AI's potential to uncover unexpected insights from existing data, generating new scientific questions and challenging prevailing cosmological models. By revealing hidden patterns and connections, artificial intelligence could open entirely new chapters in our understanding of the universe, fundamentally altering how we perceive reality. As these telescopes come online and AI-driven analysis grows ever more sophisticated, the next decades promise a renaissance in cosmic discovery. We stand on the brink of answering age-old questions about the universe's origins, its fate, and the potential for life beyond Earth. These advances will deepen our sense of wonder and humility, reminding us how much remains unknown while inspiring humanity to continue reaching for the stars with curiosity, courage, and relentless determination. For instance, machine learning algorithms possess the extraordinary capability to uncover patterns in the cosmic tapestry that have long eluded human detection. By analyzing the vast data sets collected by space telescopes over decades, these algorithms can identify subtle signatures, hidden whispers in the data, that may indicate the presence of distant exoplanets or reveal new structures within the sprawling distribution of galaxies. As artificial intelligence and machine learning technologies evolve, their integration into astronomical research promises to accelerate the pace of discovery, transforming our understanding of the cosmos. They are not merely tools, they are revolutionaries, unlocking secrets from the cosmic depths, potentially answering some of humanity's most profound questions about our place in the universe. Current space exploration technologies, despite their many remarkable achievements, remain shackled by significant limitations that restrain our cosmic ambitions. One of the most formidable obstacles is the unfathomable vastness of space. Even the nearest stars beyond our solar system lie over 4 light-years away. This staggering distance renders interstellar travel nearly impossible with present-day technology. The immense timescales and colossal energy demands required to traverse such distances dwarf our current capabilities. The spacecraft we send out drift at speeds that seem slow in comparison to the vast cosmic ocean, restricting the majority of exploration to our immediate neighborhood, the solar system. Another critical constraint lies in our reliance on chemical propulsion systems. Despite numerous advancements, these propulsion methods still suffer from relatively low energy efficiency. They limit not only the speed and range of spacecraft, but also the payload they can carry, as a large fraction of the launch weight must be devoted to fuel alone. This fuel dependency forms a bottleneck that impedes deeper and more ambitious missions into space. The hostile environment of space compounds these challenges. Radiation permeates the void, microgravity affects human physiology and spacecraft systems alike, and extreme temperature fluctuations test the durability of every mission component. These harsh conditions present formidable barriers to manned missions beyond the Moon or Mars. Extensive shielding and robust life support systems become necessities, significantly increasing mission costs and complexity. Communication delays add yet another layer of difficulty. As missions venture to the outer planets and beyond, The time it takes for signals to travel between Earth and spacecraft extends to hours. This latency severely restricts real-time control and responsiveness, complicating critical decision-making processes and potentially jeopardizing mission success. Financial hurdles persist alongside technological ones. Despite progress in reducing launch costs, the development, deployment, and operation of space missions remain prohibitively expensive. These endeavors demand vast investments with often uncertain returns, posing ongoing challenges in securing funding and allocating resources wisely. Overcoming these formidable limitations requires innovative breakthroughs. Advanced propulsion technologies, such as nuclear, thermal, or electric propulsion, promise to boost spacecraft speeds and extend mission ranges. Autonomous systems capable of managing spacecraft operations independently will reduce reliance on delayed human commands. International collaboration stands as a beacon of hope, pooling financial and technological resources across nations to share the burdens of exploration. Looking ahead, the future of space exploration holds tantalizing prospects. Missions to asteroids and comets are poised to unlock the mysteries of our solar system's origins and early history. These celestial bodies, remnants from the birth of our solar system over 4.6 billion years ago, serve as time capsules, preserving pristine materials from that primordial era. Asteroids, primarily residing in the belt between Mars and Jupiter, consist of rocky and metallic debris that never formed into a planet, largely due to Jupiter's immense gravitational influence. Investigating their composition sheds light on the processes that shape the terrestrial planets and the distribution of matter in the early solar system. Comets, composed of ice, dust, and complex organic compounds, hail from the distant, colder regions of the solar system. Their nuclei safeguard volatile materials that have remained frozen in the deep cosmic freeze, offering clues about the outer reaches of the solar system and the potential role these icy wanderers played in delivering water and organic molecules to Earth. This delivery may have been a crucial factor in the emergence of life on our planet. Future missions equipped with advanced instruments aspire to collect samples from these ancient visitors and return them to Earth. Analyzing these samples in detail could reveal exact isotopic ratios and the presence of complex organic molecules, unveiling insights into the primordial conditions and chemical processes at work during the solar system's formation. These missions promise not only to deepen our knowledge of where we come from, but also to guide our exploration toward the stars that lie beyond, beckoning us to uncover even greater cosmic secrets. In addition, by closely observing the physical and chemical processes unfolding on asteroids and comets, such as outgassing behaviors, intricate interactions with the relentless solar wind, and the dramatic effects of collisions, scientists unlock invaluable insights into the vast and complex dynamics governing our solar system's evolution. These small celestial bodies, often seen as mere cosmic debris, are in fact living records, frozen snapshots of the primordial materials and forces that shaped the planets and stars we know today. Studying these phenomena reveals not only the history etched in their rocky and icy surfaces, but also the mechanisms that continue to drive change across the solar system's architecture. And exploring the vast, uncharted territories of space demands nothing less than groundbreaking innovation in technology. Pioneering advances in propulsion systems, life support frameworks, and space habitat design form the foundation upon which humanity's ambitions to travel beyond the Moon and Mars depend. Beyond these familiar neighbors lies a sprawling expanse, millions to billions of miles away, where the very scale of distance challenges current human ingenuity. To bridge these cosmic gulfs, revolutionary propulsion technologies become paramount. Traditional chemical rockets, though powerful and reliable, fall short in efficiency and speed for such deep space journeys. Thus, researchers are relentlessly developing alternative propulsion methods like ion thrusters and nuclear thermal propulsion, technologies that promise to slash travel times and open the gateway to distant planets and beyond. And at the heart of sustained human presence in space lies the challenge of creating life support systems capable of nurturing astronauts for years, not just days or months. These systems must transcend basic survival, evolving into highly efficient closed-loop ecosystems that recycle air, water, and food with extraordinary precision, minimizing the reliance on costly and logistically complex resupply missions. Such sustainability is crucial to long-duration missions, where every resource conserved can be the difference between mission success and failure. Simultaneously, the design and construction of space habitats capable of shielding explorers from cosmic radiation, extreme temperature fluctuations, and microgravity's effects are fundamental. These habitats must provide Earth-like conditions, comfort, safety, and psychological well-being through cutting-edge materials science and modular architectural design, transforming stark spacecraft interiors into viable homes away from home. Moreover, these technological advancements collectively pave the way for humanity's next giant leap into the cosmos, unlocking mysteries that lie far beyond our current reach. The evolution of space travel technology fundamentally transforms our capacity to search for extraterrestrial life, extending the boundaries of where and how we explore. Each breakthrough enables deeper and more precise probes into the cosmos, reaching realms that were previously inaccessible. For example, the deployment of increasingly powerful telescopes equipped with sophisticated remote sensing instruments allows astronomers to detect exoplanets orbiting distant stars, analyze their atmospheric compositions for biosignatures, and identify those situated within habitable zones, regions where liquid water and Earth-like conditions might exist. And on the surfaces of planets and moons within our solar system, cutting-edge rovers and landers, armed with state-of-the-art onboard laboratories, traverse alien landscapes searching for biosignatures or markers of past or present life. Missions to Mars, Europa, Titan, and other intriguing worlds have been enabled by leaps in robotics, artificial intelligence, and propulsion technologies. Each data point collected from these exploratory endeavors deepens our understanding of the delicate balance of environmental conditions necessary for life to flourish and expands our appreciation of life's potential diversity beyond Earth. Furthermore, the pursuit of innovative propulsion techniques such as ion drives and solar sails offers the tantalizing possibility of drastically accelerating space travel. These methods could one day enable the dispatch of probes to the farthest reaches of our galaxy and even beyond, opening windows to cosmic territories previously deemed unreachable. With each stride in propulsion innovation, the dream of discovering extraterrestrial life inches closer to reality, pushing us to expand not only our technological boundaries, but also the very scope of our curiosity and understanding about life in the universe. And yet, while exploring the visible cosmos captures much attention, the elusive nature of dark matter and dark energy, components believed to constitute an overwhelming majority of the universe's mass energy content, remains one of the greatest scientific enigmas. For decades, these unseen forces have puzzled physicists, hiding behind the veil of invisibility. However, with the horizon of technology ever advancing, new methodologies are emerging that hold promise to unravel these cosmic mysteries. Among the most hopeful approaches is the development of highly sensitive detectors designed to directly observe the elusive particles that might make up dark matter, such as weakly interacting massive particles, WIMPs. Experiments like the Large Underground Xenon detectors push the limits of direct detection by employing liquid xenon to capture the faintest interactions between dark matter particles and ordinary matter. Simultaneously, to confront the enigmatic force known as dark energy. Thought to drive the accelerating expansion of the universe, scientists deploy advanced telescopes and observatories equipped with state-of-the-art instruments capable of mapping the cosmos with unprecedented precision. Projects such as the Dark Energy Spectroscopic Instrument, DSSI, aim to construct a comprehensive three-dimensional map of the universe by observing millions of galaxies and tracing how their distribution evolves over cosmic time. By analyzing these vast data sets, researchers can infer the properties of dark energy and its profound influence on the very fabric of space-time. Moreover, gravitational wave detectors such as LIGO and Virgo, already triumphant in capturing ripples caused by colliding black holes and neutron stars, may also serve as novel probes into the realms of dark matter and dark energy. By examining how these invisible forces alter the propagation of gravitational waves, scientists hope to glean new insights that could revolutionize our understanding of the universe's underlying structure and destiny. While the direct detection of dark matter and the precise characterization of dark energy remain towering challenges, the technologies and experiments pioneering this frontier shine as beacons illuminating the path towards some of the most profound discoveries in physics. These discoveries promise not only to reshape our grasp of the universe's structure, but also to redefine humanity's place within it, deepening our cosmic narrative and expanding the horizons of scientific knowledge. In every sense, the relentless pursuit of knowledge, from the microcosm of asteroid outgassing to the vast expanse of cosmic dark energy, forms the grand tapestry of modern space exploration, weaving together the dreams, technologies, and unyielding curiosity that propel us onward into the unknown. Quantum computing, with its revolutionary approach to processing information, holds immense potential to transform our ability to simulate and understand the intricacies of the universe. Unlike classical computers, which process bits of information as either zeros or ones, quantum computers utilize quantum bits or qubits, which can represent and process a vast amount of information simultaneously due to the principles of superposition and entanglement. This leap in computational capacity could dramatically enhance our ability to model complex systems that are currently beyond the reach of classical computing. In cosmology and astrophysics, for example, quantum computing could enable the simulation of the universe at an unprecedented scale and detail, from the behavior of galaxies to the interactions between fundamental particles. It could offer insights into the mysteries of dark matter and dark energy by allowing for simulations that accurately represent their effects on the cosmos. Moreover, in the realm of particle physics, quantum computing may facilitate the exploration of the quantum vacuum and the fundamental forces of nature, potentially unveiling new particles and interactions. Additionally, quantum computing could significantly advance our understanding of quantum mechanics itself, allowing for simulations of quantum systems that are inherently difficult for classical computers to handle. This includes complex quantum phenomena such as superposition, entanglement, and quantum tunneling, which are pivotal for unlocking deeper truths about the fabric of reality. By providing the tools to tackle these computational challenges, quantum computing not only promises to extend our scientific knowledge, but also to solve some of the most profound and perplexing questions about the universe and our place within it. As technology marches forward, the synergy between quantum computing and the physical sciences stands as a testament to humanity's enduring quest for understanding. The deployment of powerful artificial intelligence, AI, in space exploration brings forth a host of ethical considerations that must be carefully navigated. One primary concern is the autonomy of AI systems. As we entrust AI with more critical tasks, from piloting spacecraft to making decisions during exploratory missions on distant planets, the question arises, to what extent should AI operate independently? Ensuring that these systems can make safe, ethical decisions without human oversight, especially in unforeseen situations, is paramount. Another ethical consideration is the preservation of extraterrestrial environments. As AI technologies enable us to reach and potentially interact with previously untouched worlds, we must consider our impact on these celestial bodies. The principle of planetary protection aims to prevent biological contamination, safeguarding not only the scientific integrity of our explorations, but also any potential ecosystems that might exist. The directive to do no harm extends beyond Earth, urging us to use AI responsibly to preserve the pristine nature of these environments for future research and the potential for life. Data privacy and security represent additional ethical challenges. Space exploration generates vast amounts of sensitive data, from the mapping of distant planets to the detailing of potential resources. Ensuring the privacy and security of this data against misuse, especially when AI is involved in processing and analyzing this information, is critical. Furthermore, the equitable sharing of knowledge and resources discovered through AI-assisted space exploration raises questions about accessibility and the democratization of space science. Lastly, the ethical development and deployment of AI in space exploration call for transparency, accountability, and inclusivity. This includes collaborating across nations and cultures, involving a diverse set of stakeholders in decision-making processes, and ensuring that the benefits of space exploration enhanced by AI are shared widely and equitably. As we stand on the precipice of a new era in space exploration propelled by advancements in AI, it is essential that ethical considerations guide our journey, ensuring that we explore responsibly and conscientiously with respect for the unknown and the integrity of the cosmos at the forefront of our endeavors. International collaborations play a pivotal role in enhancing our capabilities to study the universe, leveraging the collective resources, expertise, and perspectives of the global scientific community. Such partnerships allow for the pooling of financial and technological resources, which is crucial for launching ambitious projects that would be beyond the reach of any single nation. For instance, the construction and operation of large-scale facilities such as the Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, or the upcoming Square Kilometer Array, SKA, set to be built in Australia and South Africa, are made possible through international consortia. These powerful observatories provide unparalleled insights into the cosmos, from the formation of stars and planets to the detection of complex molecules that could hint at life's building blocks. In addition to resource sharing, international collaborations foster a diverse scientific community, bringing together a wide range of expertise and research traditions. This diversity is invaluable in developing innovative approaches to research and problem solving, leading to breakthroughs that might not occur within more homogeneous or isolated research environments. It also offers opportunities for cross-training and education, preparing a new generation of scientists with a broad global perspective on cosmic exploration. Moreover, international partnerships in space exploration embody a shared spirit of curiosity and discovery that transcends geopolitical boundaries. They can act as bridges between nations, fostering peaceful cooperation and mutual understanding amidst a quest that unites humanity, comprehending our place in the universe. By working together, countries can also address common challenges such as space debris management and the responsible use of space, setting standards and protocols that ensure a sustainable future for space exploration. Ultimately, international collaborations in the study of the universe not only maximize our scientific return, but also serve as a beacon of human unity, inspiring us to reach beyond our earthly divisions and to embrace the cosmic journey together. In this grand endeavor, the intertwining of quantum computing, artificial intelligence, ethical responsibility, and global cooperation shapes the future of exploration, opening doors to mysteries once thought unreachable, and affirming humanity's timeless curiosity and determination to understand the cosmos in all its vast complexity, but also remind us of our shared humanity, highlighting how much more can be achieved when we unite in the pursuit of knowledge beyond our world. The discovery of evidence pointing to past universes would represent a monumental shift in our understanding of cosmology and the very nature of reality itself. It would imply that our universe is not the singular, isolated event we once thought it to be, but rather a link in an immeasurably vast chain of cosmic existence. Such a finding would lend weight to theories like the Cyclic universe model, which posits that the universe undergoes an infinite series of expansions and contractions, or the multiverse theory, suggesting the existence of multiple or even an infinite number of universes. From a scientific perspective, this discovery would propel an unprecedented revolution in physics, prompting a re-evaluation of the fundamental laws that govern the cosmos. The insights gained could potentially resolve long-standing puzzles, such as the nature of dark matter and dark energy, the reasons for the apparent fine-tuning of the universe for life, and the initial conditions that led to the Big Bang. Theoretical frameworks that until now have been purely speculative could find concrete support, pushing the boundaries of science into new, uncharted territories. On a philosophical and existential level, evidence of past universes would profoundly alter our perspective on our place within the cosmos. The realization that our universe is but one of many could have a humbling effect, expanding our cosmic perspective and challenging deeply held beliefs about the universe's origin and ultimate fate. Moreover, it could open up new contemplations on the nature of time, causality, and the possibility of life and civilization in these other universes. In practical terms, such a discovery would likely galvanize public and scientific interest in further explorations of the cosmos, potentially leading to increased funding and international cooperation aimed at unlocking the mysteries of the universe. It would underscore the importance of space exploration and astrophysical research, not just for gaining knowledge about our own universe, but for understanding the broader cosmic landscape in which it resides. Ultimately, finding evidence of past universes would be one of the most profound discoveries in human history, expanding our knowledge of the cosmos in ways we can hardly imagine and forever changing our understanding of reality. The concept of time, one of the most enigmatic and fundamental aspects of the universe, undergoes fascinating variations across different cosmological models, reflecting the diverse ways in which scientists and philosophers understand and interpret the cosmos. In the standard Big Bang model, time is considered to begin at a singular point approximately 13.8 billion years ago, initiating the expansion of the universe from an infinitely dense state. Here, time is linear, unfolding in a singular, unidirectional manner from the moment of the Big Bang to the present and extending into the future. However, in other cosmological models, the nature of time can be strikingly different. For example, in the cyclic or oscillating universe models, time might not have a clear beginning or end. Instead, it may loop endlessly through phases of expansion and contraction, each cycle potentially birthing a new universe from the ashes of the last. This cyclical vision of time challenges the traditional narrative of a linear timeline and invites us to rethink the very fabric of existence itself. In the realm of the multiverse, time could be a fragmented or multidimensional phenomenon, varying across different universes with their own distinct timelines and physical laws. The implications of such models extend far beyond physics, touching upon questions that have captivated human thought for millennia. What is the true nature of reality? How does time shape our existence? And could life, intelligence, and consciousness arise in realms completely alien to our own? As we stand on the threshold of these profound questions, the pursuit of evidence for past universes represents more than a scientific endeavor. It is a testament to humanity's boundless curiosity and resilience, a collective journey that unites us in the quest to understand our place in the infinite expanse of existence. Each step forward in this cosmic exploration draws us closer, not only to the secrets of the universe, but to a deeper awareness of ourselves, our shared humanity, and the extraordinary potential that lies in the unity of human endeavor. Through collaborative international projects, advanced technologies, and the relentless spirit of inquiry, we inch ever closer to uncovering these cosmic truths. The discovery of past universes, far from being an isolated scientific milestone, would ripple through society, inspiring new philosophies, art, and ways of thinking that embrace the grandeur and mystery of the cosmos. As we imagine a universe not singular, but part of an infinite chain, the horizon of human knowledge expands exponentially. This understanding transforms our sense of identity from isolated beings on a pale blue dot to participants in a vast, ongoing cosmic saga, an endless dance of creation, destruction, and rebirth, where the mysteries of the universe continually unfold, inviting us to explore, to question, and to dream beyond the confines of our current reality. But instead, it is part of an eternal dance, a vast cosmic cycle of expansions and contractions that ripple across the fabric of existence. Each cycle, though it may seem to mark a clear beginning and end, is merely a fleeting phase within an infinite sequence. This challenges everything we believe about linear time, suggesting that time itself is not a straightforward arrow, but a flowing, cyclical phenomenon woven into the cosmos. The complexity deepens with the idea of the multiverse, a staggering concept where countless universes exist simultaneously yet independently. In these diverse realms, each universe carries its own unique timeline, governed by its own laws of physics, which might differ dramatically from ours. Could time flow faster in one universe or slower in another? Might it even run backwards somewhere beyond our grasp? These questions push the boundaries of our understanding, as we grapple with the possibility that the flow and nature of time are not universal constants, but local phenomena that shift and morph in strange and unpredictable ways. Turning to the cutting-edge frontiers of physics, String theory and quantum gravity offer even more tantalizing glimpses into the essence of time. They propose that space and time might not be fundamental, indivisible entities, but instead emerge from deeper, pre-geometric quantum states. Imagine a world beneath the world, a realm where what we call time and space are just the surface ripples of something far more mysterious and profound. In this frame, time is not a primary player in the cosmic stage, but a secondary character born from the interactions of underlying quantum elements that defy classical intuition. Such radically different conceptions force us to reconsider the very fabric of reality itself. Time is no longer a static, universal backdrop against which events unfold like a simple movie reel. Instead, it becomes a dynamic, vital thread interwoven with the universe's structure, a key to understanding the cosmic tapestry and our place within it. As our scientific models grow ever more sophisticated, so too does our grasp of time's true nature, hinting at deeper truths that might forever alter our worldview. The notion that our entire universe might be a simulation, a complex, digital construct overseen by some higher intelligence, moves these contemplations into a realm where science, philosophy, and speculative fiction intertwine. Inspired by the exponential growth of computational power and virtual realities, this hypothesis raises provocative questions. Is everything we perceive, every sensation and experience, just lines of code in an advanced simulation? While proving such a theory is profoundly difficult, as any proof would itself be embedded within the simulation's constraints, some researchers seek subtle signs. Tiny glitches in physical laws or unexplained irregularities in fundamental constants that might betray the artificial architecture of our reality. Others explore the idea that, like any digital construct, our universe might have a finite resolution, a minimal granularity in space and time comparable to pixels on a screen. High-energy physics experiments, pushing the boundaries of particle accelerators and quantum probes, aim to detect such limits, searching for the fingerprints of a computational substrate beneath reality's surface. Quantum mechanics adds yet another layer of mystery, with phenomena such as entanglement and the observer effect hinting at an underlying algorithmic process. The fact that quantum systems seem to depend on observation, collapsing probabilities into realities, resembles the way a computer might render information dynamically as it is accessed. Despite these fascinating leads, the challenge remains daunting. The self-contained nature of a simulated universe implies that any evidence we discover could be nothing more than part of the program itself, making conclusive proof elusive, if not impossible. Philosophically, the simulation hypothesis pushes us to confront profound questions about consciousness, free will, and the essence of existence, blurring the boundaries between reality and illusion. Without definitive evidence, this idea remains a powerful thought experiment, a lens through which we examine the limits of knowledge and the mysteries of existence. It forces science and philosophy to grapple with questions once considered purely speculative, encouraging a deeper inquiry into the foundations of reality and what it means to be alive. Parallel to this, theories of multiple timelines spring forth from the fertile ground of quantum mechanics and science fiction alike. Imagine a universe where every choice, every flicker of quantum chance, spawns a new timeline, a branching tree of realities where every possible outcome is realized. This sprawling multiverse disrupts the comforting idea of a single, linear path through time, replacing it with a complex, intertwined web where countless versions of the universe and of ourselves exist side by side. Such a vision reshapes our understanding of reality itself. If infinite versions of existence coexist simultaneously, what does it mean to have a singular experience? How do we define identity or causality when every decision fractures the timeline into myriad possibilities? The deterministic universe gives way to a cosmos alive with choice and chance, where fate is not a fixed script, but an ever-expanding narrative. The profound implications extend beyond physics into philosophy and the very nature of consciousness. The multiverse challenges us to rethink our place in the cosmos, to embrace a reality far richer and more complex than the one we perceive. It invites us to explore the endless tapestry of timelines, where every path taken and every opportunity missed exists somewhere, somehow, unfolding in parallel. In all these ways, our journey through time, from the cosmic cycles of expansion to the dizzying heights of quantum speculation, reveals a universe that is endlessly mysterious and infinitely more intricate than our everyday experience suggests. The nature of time, far from settled, remains one of the greatest enigmas, inviting us to explore, question, and imagine new horizons beyond the limits of our current understanding. But a dynamic, interactive plethora of possibilities unfolds before us when we delve into the notion of multiple timelines. This concept does not merely extend our understanding of time, it profoundly disrupts it, igniting a cascade of intriguing questions about the essence of personal identity. If multiple versions of an individual exist across these divergent timelines, each living out distinct choices and encountering unique outcomes, then which one stands as the true self? This question, far from simple, shatters the comforting idea of a singular, consistent identity. Instead, it points toward a fluid, multidimensional conception of selfhood, one that is contingent, shifting according to the particular timeline one occupies. Within this sprawling multiverse of possibilities, the ethics of decision-making morph into something far more complex and layered. If every choice creates a branching universe, what responsibility do we hold for the consequences rippling through these parallel realities? Are we accountable solely for the outcomes within our own timeline, or must we grapple with the moral weight of actions carried out by our alternate selves across infinite versions of existence? This expanding ethical landscape challenges traditional notions of accountability, forcing a re-examination of how we conceive the ramifications of our decisions, not just locally, but universally. Simultaneously, the existence of multiple timelines reshapes our understanding of causality and free will. The idea that every conceivable outcome manifests somewhere in the multiverse suggests free will is not an illusion, but an intrinsic feature of reality itself, where each decision genuinely alters the trajectory of some branch of existence. Yet, this brings forth a paradox. If every possible outcome does indeed transpire, can free will truly exist as a meaningful concept? Or is it merely an intricate dance within an all-encompassing deterministic framework where every path is preordained yet experienced as choice? Grappling with these questions pushes us to reconsider the very fabric of existence, inviting profound philosophical reflection that challenges long-standing assumptions about time, reality, and our role in the cosmos. Exploring these ideas deepens our understanding of both the universe and ourselves. It stretches the boundaries of human thought, beckoning us toward new frontiers of inquiry. Within the realm of theoretical physics, concepts like extraspatial dimensions, quantum entanglement, and the malleable nature of space-time offer frameworks that could one day illuminate phenomena currently dismissed as paranormal. Though mainstream science cautious and skeptical, demanding empirical evidence and reproducibility, the speculative edges of physics invite open-minded consideration of realities beyond ordinary perception. Theories proposing extraspatial dimensions beyond the familiar three, as articulated in string theory and other high-energy physics frameworks, radically expand our conception of space. These hidden dimensions might harbor the key to understanding mysterious phenomena such as ghosts or apparitions, suggesting that what we label paranormal could be fleeting interactions with or glimpses into extra-dimensional realms coexisting alongside our perceptible universe. This idea injects a tangible scientific curiosity into the realm of the unexplained, pushing the envelope of what might be possible. Quantum entanglement, famously described as spooky action at a distance, reveals a phenomenon where two particles instantaneously influence each other's states, regardless of spatial separation. This defies classical intuitions about causality and locality, prompting speculation that entanglement might underlie experiences like telepathy or synchronous events, where information seemingly transmits beyond known physical mechanisms. The enigma deepens when considering the role of the observer in quantum mechanics, particularly within the Copenhagen interpretation. The observer's measurement determines the outcome of quantum events, linking consciousness intimately with the fabric of reality itself. This connection has inspired hypotheses that consciousness might be a fundamental universal property, potentially accounting for phenomena such as precognition or psychokinesis, where the mind exerts direct influence over physical systems. Theoretical constructs such as wormholes, arising from solutions to Einstein's equations of general relativity, introduce the possibility of shortcuts through spacetime. These speculative tunnels could theoretically explain anomalies like time slips, moments when the flow of time appears disrupted or nonlinear. While such concepts face daunting theoretical and practical challenges, they tantalize with the prospect of bending the known rules of causality, revealing the universe as far stranger and more intricate than our everyday experiences suggest. Together, these ideas weave a narrative of a cosmos that is fluid, multifaceted, and brimming with mysteries. They invite us not only to question the nature of reality, but to embrace the astonishing possibilities that lie beyond the veil of current understanding. In this grand quest, human curiosity, imagination, and rigorous scientific exploration converge, driving us ever closer to uncovering the profound truths about existence, consciousness, and the infinite landscapes of time itself. They offer intriguing possibilities for reinterpreting experiences traditionally labeled as paranormal through the extraordinary lens of advanced physics. And while these speculations ignite the imagination, it is crucial to underscore that they are not embraced as scientific explanations for paranormal phenomena by the mainstream scientific community today. Instead, they reside in a fascinating space where theoretical physics intersects with human curiosity about the unknown. The stringent demands of scientific rigor, evidence, reproducibility, and falsifiability require us to proceed with caution before drawing any firm conclusions from these hypotheses. Yet, history teaches us that what once seemed heretical in science often transforms into accepted truth over time. This legacy serves as a powerful reminder of the importance of maintaining an open, yet critically discerning mind toward the enigmas that still lie beyond our grasp. In the vast and mysterious realm of cosmology, the boundaries of human knowledge are continually stretched by technological advances and groundbreaking theoretical insights. Despite this progress, profound questions persist, challenging our current frameworks and capabilities. Consider dark matter and dark energy, together accounting for approximately 95% of the universe's total mass energy content, yet remaining stubbornly elusive. Our inability to detect dark matter particles directly or fully comprehend the accelerating expansion of the cosmos attributed to dark energy starkly exposes the substantial gaps in our understanding of the universe's fundamental constituents. The Big Bang Theory stands as a remarkably robust scaffold, explaining the universe's evolution from a searingly hot, dense primordial state. However, the exact nature of the initial singularity, the point from which space and time themselves are believed to have emerged, remains an impenetrable mystery. Quantum effects are expected to dominate this embryonic moment, but without a complete theory of quantum gravity, our grasp of these conditions is incomplete. The quest for such a unifying theory, which seamlessly reconciles general relativity with quantum mechanics, is one of the most formidable challenges in contemporary physics. Current cosmological observations suggest that the universe is expanding at an accelerating rate. Still, the ultimate fate of the cosmos depends on several factors, including the true nature of dark energy and the possibility that the fundamental laws of physics might evolve over immense timescales. Will the universe continue expanding forever, cooling into a bleak and desolate big freeze, or will it eventually halt and collapse in a dramatic big crunch? Or perhaps it will encounter a fate yet unimagined by our current theories. These questions linger as profound open enigmas at the heart of cosmological research. Adding further layers of intrigue is the concept of a multiverse, the hypothesis that our universe is but one among a potentially infinite collection, each with its own distinct physical laws and constants. This idea opens vast realms of possibility and expands our understanding of existence beyond the familiar. Yet, it also presents staggering challenges, primarily because verifying the existence of other universes seems at present almost impossible. Whether empirical evidence for a multiverse can ever be obtained remains one of the most provocative and controversial boundaries in cosmological inquiry, straddling the line between physics and philosophical speculation. The puzzle of what happens to information that falls into a black hole epitomizes the profound mysteries at the frontier of physics. This question touches on the fundamental nature of reality itself. Theoretical advances, including Stephen Hawking's groundbreaking proposals on black hole radiation, hint at deep and unexpected connections between gravity, quantum mechanics, and thermodynamics. These insights suggest that our current understanding of physics may require foundational revision to fully capture the complexity of the cosmos. Each of these profound mysteries at the edge of human knowledge highlights not only the limitations of our current theories and technologies, but also offers tantalizing glimpses into the vast unknown. They stand as beacons, illuminating the path forward, like beckoning us to continue probing the cosmos with relentless curiosity and intellectual courage. In exploring these questions, we are reminded that the journey of discovery is far from over, and that the universe, in all its grandeur and enigma, still holds secrets that may forever challenge and expand the horizons of human understanding. But a frontier for future exploration emerges, promising that the journey of discovery in cosmology is far from complete. Yet, the tantalizing possibility of undiscovered forces of nature presents a profound challenge and opportunity within physics, holding the potential to revolutionize and redefine our understanding of the cosmos at its most fundamental level. Throughout the sweeping tapestry of history, the unveiling of new forces such as electromagnetism and the weak and strong nuclear forces has not only transformed physics, but sparked paradigm shifts that reconfigured how humanity comprehends the universe and its governing laws. Today, whispers and hints within the fabric of scientific observation suggest that our current model of physics, despite its extraordinary success, might represent only a partial glimpse of a much grander reality. The enigmatic mysteries surrounding dark matter and dark energy, which together constitute an overwhelming majority of the universe's mass energy content, beckon us toward the possibility of forces or particles beyond the reach of the standard model of particle physics. This model, while remarkably robust, fails to incorporate gravity into its framework and leaves unexplained the profound imbalance between matter and antimatter that permeates our universe. These gaps in understanding illuminate the limits of our present knowledge and underscore the compelling need to venture further. In the relentless search for new forces, scientists turn their attention both skyward and inward, scrutinizing anomalies and deviations in physical behavior, whether observed on cosmic scales or under the controlled conditions of particle accelerators. Minute discrepancies in particle behavior that defy predictions of the standard model could serve as signposts pointing toward undiscovered forces. Similarly, perplexing astrophysical phenomena observed at immense scales may reveal forces acting across vast cosmic distances or interactions involving dark matter that cannot be explained by gravity alone. The potential detection of a new fundamental force would demand a seismic revision of the standard model, possibly culminating in a unified theory that encompasses not only the four known forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, but any newly discovered interactions. Such a breakthrough would not only resolve enduring enigmas of physics, but also unlock fresh avenues of research with profound implications, ranging from unveiling the very origins of the universe to inspiring revolutionary technologies grounded in novel physical principles. Physicists pursue these elusive forces by combining meticulous precision measurements of established phenomena with bold exploratory experiments that probe the outer edges of current theoretical frameworks. This endeavor is as much about rigorously testing the boundaries of our existing models as it is about uncovering new facets of nature. It exemplifies the dynamic, ever-evolving nature of scientific inquiry. The pursuit of undiscovered forces stands as a testament to the extraordinary depth and complexity of the cosmos, inviting humanity to continually expand the horizons of knowledge. Balancing scientific speculation with empirical science and cosmology requires navigating a delicate line between imagination and evidence. This task is not only challenging, but absolutely essential for advancing the field. Cosmology confronts phenomena that often lie at the very limits of human observation and comprehension, demanding a seamless fusion of theoretical innovation and stringent empirical validation. Speculation is not idle fantasy. It plays a crucial role in formulating hypotheses and conceptual frameworks that stretch beyond current understanding. These speculative ideas, while firmly grounded in established physics, often transcend observable reality, proposing radical concepts such as extra dimensions, multiverses, or exotic forms of matter and energy. The creativity embedded in these speculations ignites progress, like driving the quest for empirical evidence that could confirm or refute them. The ultimate test of any speculative theory in cosmology rests on its empirical validation through careful observation and experimentation. Cutting-edge technologies, including ever more powerful telescopes, particle accelerators, and space probes, equip scientists with unprecedented tools to explore the universe with extraordinary precision and scope. Designing experiments and observations to rigorously test the predictions of these speculative theories demands a readiness to revise or even abandon ideas in light of new evidence. This balance between speculation and empirical science is sustained through the peer review process and ongoing discourse within the scientific community. Peer review acts as a critical filter, ensuring that speculative theories undergo rigorous evaluation for scientific merit, coherence with established knowledge, and empirical testability. Meanwhile, scientific discourse, through debates, collaborations, and continuous dialogue, fosters skepticism and critical thinking that are indispensable for refining theories and guiding experimental pursuits. The interplay between speculation and empirical science is inherently iterative. Theories supported by evidence become integrated into the theoretical fabric of cosmology, while those contradicted by data are modified or discarded. This iterative cycle of hypothesis, testing, and refinement embodies the very essence of the scientific method. It allows cosmology to advance as a discipline that is both imaginative and firmly rooted in reality. The ongoing dance between bold theoretical exploration and meticulous empirical scrutiny ensures that cosmology remains a vibrant and robust scientific field, continuously expanding our understanding of the cosmos while remaining anchored in observable phenomena. Consciousness, while primarily explored in philosophy, psychology, and neuroscience, intriguingly intersects with cosmology and theoretical physics in ways that challenge traditional disciplinary boundaries. The involvement of consciousness in these domains spans from interpretations of fundamental physics to deeply speculative ideas about the very nature of reality. Among the most widely discussed intersections is the role of consciousness in quantum mechanics, particularly the observer effect demonstrated by experiments such as the double-slit experiment. This effect suggests that the act of observation can influence the outcome of quantum events, prompting debates about whether consciousness itself might play a fundamental role in collapsing quantum wave functions or shaping physical reality. The anthropic principle further entwines consciousness with cosmology by proposing that the fundamental constants and laws of the universe appear finely tuned to allow for the existence of life and, consequently, conscious observers. This principle raises profound questions about the relationship between the cosmos and consciousness, hinting that the universe may be, in some sense, predisposed to foster life and awareness. Variations of the anthropic principle range from relatively modest observations about the conditions necessary for life to more speculative and controversial suggestions that consciousness holds a central place in the fabric of reality. More radical speculative theories, such as panpsychism, propose that consciousness is not an emergent property, but a fundamental aspect of all matter, implying a universe in which the boundary between conscious and unconscious entities becomes blurred. Similarly, John Archibald Wheeler's idea of a participatory universe suggests that reality is co-created through interactions between physical processes and conscious observers, dissolving the classical divide between observer and observed. In recent years, emergent theories framing the universe as an immense information processor have also intersected with notions of consciousness. These perspectives speculate that consciousness could arise naturally from the complex processing of information at a cosmic scale, envisioning the universe itself as a vast computational entity. Within this framework, consciousness emerges as an inherent byproduct of universal informational dynamics. While the inclusion of consciousness in physical theories remains highly speculative and vigorously debated, it reflects a deep and enduring human desire to understand the profound mysteries of existence. This exploration straddles the boundary between science and philosophy, emphasizing the intricate and mysterious nature of consciousness and its possible connections to the fundamental workings of the cosmos. As our knowledge of both consciousness and the universe advances, this interplay may illuminate some of the most profound questions about reality, existence, and the very essence of being. The quest to comprehend the universe stands as one of humanity's most enduring and inspiring endeavors, uniting curiosity, creativity, rigorous inquiry, and philosophical reflection. It invites us to confront mysteries that challenge the limits of our understanding and to push beyond the known into realms yet uncharted. In this journey, every discovery, every insight, and every unanswered question enriches the tapestry of human knowledge, driving forward the relentless pursuit of truth and wonder that defines the spirit of exploration itself. But it is a journey marked by inherent limits shaped by the nature of scientific inquiry, the capabilities of our technologies, and the fundamental properties of the universe itself. These ultimate limits frame the horizon of our understanding, delineating what might forever lie beyond our grasp. Imagine for a moment a vast ocean of knowledge stretching infinitely before us, but with invisible barriers set by the very fabric of reality. These barriers are not mere obstacles, but intrinsic boundaries woven into the cosmos. One fundamental limit is imposed by the speed of light. This cosmic speed limit governs the maximum pace at which information, energy, and matter can travel. Because light travels at a finite speed, there is a boundary to what we can observe, a cosmic horizon. Regions beyond this horizon are inaccessible because their light has not had sufficient time to reach us since the dawn of the universe nearly 13.8 billion years ago. This cosmic horizon creates a celestial veil, a boundary that confines our direct observational reach. It means that no matter how powerful our telescopes become, some parts of the universe will forever remain hidden, wrapped in mystery, potentially holding secrets that we may never decode. At the microscopic scale, a different kind of limitation emerges, one that challenges our classical intuitions. The Heisenberg uncertainty principle asserts that there are intrinsic limits to the precision with which certain pairs of physical properties like position and momentum can be simultaneously known. This quantum uncertainty infuses the subatomic world with a fundamental fuzziness, a haze that blurs our understanding of reality at the smallest scales. This principle does not merely reflect technological shortcomings, but rather a profound truth about the universe itself. It shapes how we comprehend the initial conditions of the cosmos, the behavior of particles, and the complex tapestry of quantum systems. Our grasp of reality at these scales is not just incomplete, it is probabilistic and inherently uncertain. Beyond these physical boundaries, the sheer complexity of the universe imposes another formidable limit. Even with the staggering advances in computational power, the challenge of modeling the universe in its full complexity remains insurmountable. The cosmos is a dance of countless particles, forces, and interactions unfolding across billions of years. Simulating every nuance, from the swirling formation of galaxies to the delicate dynamics of planetary climates, is a task that pushes the limits of human ingenuity and technology. Our computational abilities, while rapidly advancing, still struggle to capture the full scope of this cosmic symphony. The complexities of chaotic systems, nonlinear interactions, and emergent phenomena mean that our models can only approximate, never fully replicate, the intricacies of reality. These fundamental limits force us to confront profound questions. What truly lies beyond the cosmic horizon? Are there aspects of reality forever cloaked in darkness? At the grandest scale, what mysteries remain hidden beyond the speed of light's reach? And when we peer inward into the quantum realm, what secrets does the uncertainty principle conceal? Beyond these physical and observational boundaries, the enigma of life in the universe looms large. What do you think exists out there? Are we truly alone in the cosmos, or do distant civilizations thrive in far-off galaxies, sending out signals lost in the vastness of space and time? This is not merely a scientific quest, but a deeply human one, a search for our place in the cosmos, for connection beyond the stars. The journey toward understanding is as much about confronting these limits as it is about pushing past them. It is an invitation to explore, to wonder, and to keep asking the questions that define our curiosity. Let us know your thoughts in the comments below. Thanks for watching.